Great. Well, welcome everyone. Looking forward to this a lot. It's been a bit of work putting it all together, but I think we're in good shape. Letty, are you there?
I can do my best to be loud. I'm not always very good at that.
That's great.
That's
Thank
good?
you.
Okay.
Yeah.
Okay, great. Thank you very much. Well, first of all, I'm sorry I can't be there in person, but thank you for letting me join in online. My name is Letty Roach. I have actually just moved to the Alfred Wegener Institute in Germany, which is where I am now. And today I have a few slides on wave sea ice interactions and then on the SEIS community. So for a few years, amongst other things, I've been working on interactions between ocean surface waves and sea ice. This work is largely motivated by the enhanced ocean surface wave activity we've seen in the new Arctic. As the sea ice has been retreating, ocean surface wave heights have been increasing, as in this figure from Thompson et al. And these larger waves have direct impacts on Arctic communities, for example, storm surge and coastal erosion. And then Antarctic sea ice is also subject to the large swells that develop over the Southern Ocean. Waves and sea ice interact via the sea ice flow size distribution, which describes the size of these discrete pieces of sea ice that range across orders of magnitude from meters to kilometers. And we can describe them using the flow size distribution. Here I'm showing on the right, the number density of flows per flow size as captured by observations. Just emphasizing that these are existing across a really wide range of scales. The flow size distribution is determined by waves, thermodynamics, and mechanics. And then the flow size distribution in turn is what determines the amount of lateral melt that occurs on the sides of sea ice flows, and also feeds back onto how waves travel through ice, how they're attenuated, and potentially has more impacts for dynamics and other aspects as well. During my PhD, I worked on representing the flow size distribution in SEIS. So we started with the ice thickness distribution, which I think everyone will be very familiar with here, which has this equation of state. So the ice thickness distribution is determined by advection, thermodynamics, and ridging and rafting. And then in a series of papers based on one by Chris Horvath and Zipperman in 2015, we worked on representing the joint flow size and thickness distribution in SEIS. So it's kind of switching from this ice thickness distribution representation to a representation for the joint distribution, which again evolved subject to advection and thermodynamics, also the ridging and rafting, and then we added in additional physics to represent lateral thermodynamics and also wave fracture. So then in the model, the flow size distribution emerges due to the interaction of different physical processes. And we built up a description of these over a couple of papers looking at the formation of new ice, lateral melt, lateral growth, flow welding, and wave fracture. So one of the biggest challenges in all of this work was how to move forward when this flow size distribution is something that's really quite difficult to observe. There have been definitely a lot of advances in recent years. The figure I'm showing at the right is from Ellen Buckley and co-authors who developed a new tool to automatically pull out flow size information from imagery. But this is still quite in early stages, and especially towards the very small flows, the high resolution end, we have still quite limited observations, making it very hard to tune basin scale models. So where more recently we've been aiming is to try and improve the physical fidelity of different processes, and particular focusing on wave-related processes, as we've seen in previous modeling work, that these seem to have an especially large impact on the flow size distribution, especially wave fracture during the melt season. So in some recent work that's been led by Bruno Tremblay, we have been working on a new wave fracture scheme. What we have currently in SEIS is based on the Horvath and Zipperman study, which assumes that sea ice fluxes perfectly with the sea surface height field, which is based on an earlier paper where they consider two extreme limits, either assuming that the sea ice is totally flexible or it's totally rigid. And so we've been working on a new scheme where we're not making either assumption, but calculating the strain analytically by solving a conservation of momentum equation for a thin elastic plate in hydrostatic equilibrium. And here we take flow size into account. And I think we feel quite confident in this when we've been looking at the strains computed from this model. So at the right, I'm showing the strain across a flow of 200 meters in diameter and 1 meter in thickness. The strain magnitudes we get are much more, much closer to observations than with the Horvath and Zipperman approach. And I have some very, very preliminary results from this scheme running in SEIS 6 in CSM3. Here I'm showing the representative radius in a data atmosphere simulation. This is just a startup run, so it's very, very preliminary. But we seem to be capturing the representative radius quite well, as far as we can tell, with the limitations in observations. And then if we look at these plots here, show the difference between the kind of standard, the Horvath and Zipperman wave fracture scheme, and then this new scheme on the right. And you can see there's quite a big difference here in the flow size distribution, where we have, with the new scheme, many more flows at larger sizes. And I think this goes some way to improving the simulation of flow size in the Antarctic. This work has been kind of pushed through by a group of us who've been meeting regularly. So I want to give thanks especially to Dave Bailey and Cecilia Bitz and Bruno Tremblay on this. And we have a lot more to do going forwards, working on moving this into the fully coupled model, seeing where we can kind of simplify and learn, specifically looking at this wave fracture process. And then we're planning to also evaluate against observations in case study type simulations. So that was my kind of quick science update. And then I wanted to just reflect a little bit on working with SEIS and the SEIS community and Elizabeth. I started working with SEIS during the first few months of my PhD in 2016. And looking back now, having worked with a few different models, I can say, wow, this was such a great model to get started with. It was just so well put together. You can really read the code. The variables have sensible names, so you can really just look at it and understand what's going on. And it's well structured. So I certainly did spend a lot of time reading through this code and seeing all the names popping up. But yeah, the learning curve was really quite rapid, and this is really thanks to all the community efforts, I think, to make this into a model that works well for the community. The GitHub repositories started coming on during my PhD. You can see some of the main people here in this screenshot from the GitHub. And the testing and the practices that have been developed through this have always seemed to be very well thought through and made it really quite easy to contribute to the model. In 2019, Elizabeth came to visit me and my advisor in New Zealand. So this is Wellington. And together we got to work on the code. So we holed ourselves up in an office somewhere in this building, looking out at the sea, and worked on implementing the flow size distribution into SEIS 6 and IcePack. I don't really have pictures of my own from this time, but this one is from Google Maps. And then while she was visiting us, Elizabeth also went on a trip around the South Island, flying actually in a small plane herself. And so this may have been some of the views that she saw. This visit was really nice for me. Elizabeth was so hands-on with the code, really carefully thinking about and talking through all the design choices. And so I absolutely learned a lot from her during this time. And it was also very rewarding for me as a student that this very senior person was interested in what I'd done and really wanted to start working with it. So somewhat on that theme, I put this sentence in my PhD thesis acknowledgements that I have also benefited from the work done by senior women in science to break down barriers and make the scientific community a more inclusive place. The visibility of women in sea ice research inspired me to think that this was a field where I could contribute. And while I feel slightly embarrassed to read that out, it's really a very, very true statement. And it has absolutely had a big impact on me. I still have this very clear memory of sitting in the library during my master's thesis in Scotland. And my advisor at the time had just given me this stack of sea ice modeling papers to read. I was studying mathematical physics. Almost all of my lecturers were men. Almost everyone that we learned about in our lectures doing the science were men. And the stack of papers, I realized I suddenly was like, wow, these are all women. And it was really a very clear moment for me that it was yeah, I think it had a very big impact on me. And it's just, I think it's great to be part of the community with such strong female leadership. And this is something that really filters down to the whole sea ice community. And I really think it makes it such a good community to be a part of. Here we are in Santa Fe in May, where we had a really nice, well-organized and productive meeting with a lot of support for early careers. So I think we've all really benefited from Elizabeth's leadership through her many scientific contributions and just leadership in overall modeling and community efforts. And so I would just like to finish with wishing you the very best in this next phase.
Thanks so much, Letty. That's wonderful. So any questions for Letty? Anything? So, oh, there's a question on hand. Yeah. Yeah. Dave?
Oh, that was me trying to clap.
Okay. Great. Okay. All right. So Danny, are you there online?
Oh, yes, you can see and hear me now, I hope.
Yeah, we can hear you.
Okay, good. Am I going to share my slides or do you have them there? I can share if that's easier.
We've got them. We're doing them here. Do I need to load it?
Can you have him and all the virtual people present on there, and if they can, please?
Okay, sure. Can you share, Danny, from yours?
Yep, sure. Well, I mean, I can install. Let's see if I actually can.
It's Google Meets. It's a little different. I understand.
All right. Are you seeing the title screen now?
Yes.
Okay, good. I can no longer see you, so hopefully you're all smiling.
Okay. And then I think if you could put it into full screen mode, if possible.
Right. Is that good? It's in full screen mode on my side.
Oh, okay. I'm not sure. There's probably a delay here. So anyway, we can see it. So thanks. Go ahead.
We'll just start. Okay. All right. Well, first of all, thank you very much for inviting me to come and speak at this event. I'd like to thank the organisers as well. And of course, congratulations to Elizabeth, who has achieved a stunning amount in her career, and I'm sure will continue to do great things in her retirement. Sorry I can't be there in person. I hope you have a great day, and let me start my talk then. Okay, so this is a bit of a quick zip through some work done over the decades on melt ponds. That's melt pond in the middle. Okay, So impact of a melt pond model on sea ice simulations in past, present and future climates. I should thank the various folk I've worked with, including Elizabeth. Okay, so I'm guessing that I don't really need to tell people what melt ponds are, but as an aide-memoire, as the snow and upper layer of sea ice melt in the spring and summer, meltwater collects on the surface of the sea ice. Ponds, 100 meters maybe wide, 50 centimeters or so deep, and can cover a large fraction of the surface of the sea ice. You can see from the picture that they're darker than the ice and snow, and so the visible albedo is quite a lot lower when you have ponds present, and the melt rate beneath ponds is much greater. So as a consequence of this, you would imagine, and this is indeed true, that melt ponds.
Danny, I'm sorry
Yep.
to interrupt you.
That's all right.
We aren't seeing your slides advance, so could you
Oh.
try going to full screen again, or
Okay. I was in full screen already. I don't know why you're not seeing it.
yeah, you need to, I think, toggle your screens between.
Mm. Okay, it says here, to avoid an infinity mirror, don't share your entire screen or browse a window. Share just a tab or a different window
Okay,
instead.
Paul's working on it. We've got our AV people who are doing it.
Okay.
Okay, so maybe you've been suffering from infinity mirror syndrome, or I have. Maybe I shouldn't share the entire screen. I didn't think. Actually, I didn't think I was sharing the entire screen. Why don't you just set up the slides there, and I'll tell you how to advance?
Yeah, I think we're going to present it from here and then I'll advance them for you.
Okay, so I'll stop sharing now. Okay.
Thanks.
Yeah, just. All right, so we're seeing your first slide now.
You're seeing my slides because I'm not seeing my slides now. I can guess where you are.
I'm looking at our AV guys in the room. They seem to, yeah.
Okie doke, great.
Give us
I
a
can-
there.
I can
Are you able to see
Right.
things now?
Yep.
Okay.
All right. Well,
Um,
okay. So great to be here. Congratulations to Elizabeth. Melt ponds form the surface of sea ice. They lower the albedo and contribute to the albedo feedback mechanism. And those are some pictures from Sheba, Surface Heat Budget of the Arctic field program from 1998. So you can advance the slide now, please. Okay, so not long after that, a naive young mathematical physicist joined the Earth Sciences Department in London and started to look at sea ice and the Sheba products. And I developed a model of melt ponds on sea ice with my first PhD student, Paul Taylor. And here is a schematic sketch of some of the processes we modeled. So we had the pond on top of the sea ice. We used local conservation equations for heat and salt in the sea ice to describe what's called a mushy layer. Use a two-stream radiation model, having spoken to Don Terbridge about that. And this gave us a fairly high fidelity understanding of the one-dimensional evolution of melt ponds. But that was in 1D. So if you can please advance the slide. Okay, so of course what you saw was that melt ponds on the surface of the ice were not just 1D. So we also later on with another PhD student, and we built a model of the lateral spreading of melt ponds on the sea ice surface. So essentially the idea was that meltwater would be transferred horizontally to the lowest height and it would flow through the porous sea ice or snow cover, modeled using Darcy's law. This gave us some insight into how the melt ponds spread across the surface and, compared reasonably well with the data of the day. But, this gave us physical insight into the understanding of melt ponds. And this was quite a highly idealized model. So can we please have the next slide? Okay. So of course, these models were toy models, on paper and pen, run in Mathematica, or no one uses it anymore, or MATLAB. We wanted to build a model that was suitable for inclusion to a global climate model. So we looked to the SEIS model. So one of the key problems with representing melt ponds on the surface of sea ice is that sea ice models do not represent the topography. However, sea ice models like the SEIS model do contain a sea ice thickness distribution, the area in each thickness class. So we made a bunch of assumptions. We assumed that on average the ice was in hydrostatic balance, and so therefore constructed a surface height distribution, which is still not a topography. But we then simply assumed that wherever you were on the ice, there was ice of lower height around it, okay, or unless you're at the lowest place, and the meltwater was spread horizontally and essentially collect on the lowest ice first. And this was basically the basic principle of how you distributed meltwater on the surface of ice. So this was a MATLAB code constructed by Daniel Flocco, myself. So still not a climate model. So can we advance the slide, please? Okay, so we started speaking with Elizabeth, and with a fair bit of technical work, which she was a huge help on, we managed to go from essentially our MATLAB model of how melt ponds form into a module that can be was brought into the SEIS model. So the basic principles are the same. Meltwater collects an ice of lowest height. Hydrostatic balance is maintained. We calculate vertical drainage using Darcy's law of vertical permeability depending upon the interior solid factor of the ice. Elizabeth's help was crucial in representing meltwater as a tracer on the surface. So that was a real big step forward. And some other bits and bobs as well, including melt pond refreezing. So this finally brought like a representation into the sea ice component of the climate model. Next slide, please. So here are some simulations from what we call a standalone simulation. So the SEIS model is run with atmospheric forcing and ocean forcing. And what's being shown in the middle plot is the melt pond fraction of sea ice throughout the summer season. And the blue, orange, and red thick lines are the melt pond evolution in the 80s, 90s, and 2010s. So what you can see, if you go from blue to orange to red, is that as the decades progress, the melt pond fraction, the peak melt pond fraction is increasing. The orange dashed line and the red dashed line correspond to a particularly cold year, 1996, which had a relatively high sea ice extent, and a relatively warm year, 2012, which at the time was the sea ice minimum. Okay, so you can see there you had a relatively high melt pond fraction in that situation. Next slide, please. So this correlation between anomalies of melt pond fraction and September sea ice extent gave us an idea that the melt pond fraction could be used to somehow predict the sea ice extent. So what we found was that there was a strong correlation between the spring melt pond fraction and the subsequent September sea ice minima. So we found that correlation. Okay, lots of things are correlated, but in particularly, this enabled us to have a predictive model. So we would look at the melt pond fraction in our simulation and predict the real sea ice extent in the real world in September. So we did that with success. It was skillful. Just a correlation does not imply skill, but we did determine skill here. So the reasons behind this are what you might expect. The melt pond fraction model corresponded to where the ice was thin, but also to where you had melt taking place. And of course, you're triggering the albedo feedback mechanism here. So we believe these are the reasons. And since this paper in 2014, we've been contributing to the NSIDC Sea Ice Prediction Network. Next slide, please. Okay, so I then spoke to some of my colleagues at the Met Office in the UK, and they were pretty keen. So we brought this melt pond model into the Hadley client model, HadGem 3. So this required some changes because they were not using the Delta Eddington albedo scheme. They're using a simpler scheme, shall we say. But anyway, that was done. That was some technical work that we should. Next slide, please. So now I want to bring us up closer to the present day, but also slightly paradoxically in the deep past. So this isn't really my general area of research, but something that I was sort of brought into. In the last interglacial, which is around 120,000 years ago, it's believed the Arctic was a fair bit warmer than the pre-industrial period. And various isotope measurements and marine sediments imply that the Arctic was ice-free then, as well as it being rather warm. Previous climate models hadn't captured this. So previous climate models hadn't captured either the high temperatures or the loss of Arctic sea ice back in the last interglacial. But this climate model, which now included our melt pond scheme, did. So you can see the blue versus orange here. Okay, so this is the climatology from a 200-year simulation, and Marina Garino found that the Arctic was ice-free in the last interglacial in a model which includes our melt pond scheme. Okay, so that's interesting, but of course that model included lots of other stuff as well. Was it due to the melt ponds? Next slide, please. So to try to see whether the melt ponds were contributing significantly to the ice-free Arctic conditions in the last interglacial, a set of numerical experiments were set up, and these are reported in the paper by Diamond et al. Okay, so Rachel Diamond did most of the heavy lifting here. Okay, she's a PhD student, BATS, but they're co-supervised by Dave and myself and others. So she considered 3 different melt pond schemes. One was our melt pond scheme, which was sometimes called the Topo scheme. One which was an implicit pond scheme, which was sort of tuned to observations and had a temperature-dependent albedo. And the third scheme was to have no ponds at all. Okay, so no ponds really. And the 3 forcing scenarios were pre-industrial, so 1850 forcing. Those correspond to the last interglacial. Okay, so greenhouse gases were below present, but the orbital changes meant you had a higher top of atmosphere solar installation. And the near future, which was essentially repeating 2014 conditions, atmospheric compositional conditions going forward. So these were 3 100-year runs. So next slide, please. So this is the pre-industrial. So blue is no ponds, orange is with the R pond scheme, and green is with the tuned pond scheme. So what you can see is that including ponds significantly reduces the September sea ice extent in the pre-industrial period. Okay, but also the R pond scheme and the tuned scheme are sort of roughly equal magnitudes of sea ice extents in the pre-industrial period. Next slide, please. Now, if you go to the last interglacial, you have a different story. If you have no ponds, that's the blue curve, you have a lot of sea ice. Okay, but if you have ponds in them, you have much less sea ice. But particularly if you have the pond scheme that we developed, which was kind of a more physical scheme, you have very little sea ice indeed. So it seems here you're cleanly comparing simulations with and without our pond scheme and a simpler pond scheme, and it has a dramatic impact on the Arctic sea ice extent. Next slide, please. And this is the future. Okay, well, 2014 repeated 100 times. Okay, so you're seeing again that the, in quotes, more sophisticated or physical melt pond scheme leads to much less sea ice than the scheme which has been tuned to roughly contemporary conditions. So clearly the pond scheme you're using has a big impact. Next slide, please. Okay, there I'd like to conclude. So 24 years after Sheba, efforts of many people with diverse skills has led to a relatively sophisticated melt scheme brought into GCM simulations. And one of those people was Elizabeth. We should thank Elizabeth for that. Meltpool models have led to proven skill in seasonal CS predictions, and it's now also been unequivocally shown that climate simulations of CS are a very sensible representation of meltpool processes. So I'd just like to conclude my last point was that since Sheba, there's been a new field experiment called Mosaic. Okay, and I anticipate this being the happy hunting ground for trying to improve models going forward in the future. Okay, with that, I'd like to stop. Thank you very much.
Thanks, Danny. I apologize for the confusion here with the presentation, but any quick questions for Danny? Anyone online? Okay. All right, well, thank you. Let's see. Till, are you there?
Yes, I'm here.
And if you could stop. Oh, he's sharing for you.
I can try to share.
Yeah, it'd be good if
Lisa.
you can share, because then you can control your slides appropriately. Hopefully we can get it into full screen mode.
Can you see it?
Yes, perfect. Okay, go ahead.
Okay, thank you, and thank you for letting me talk at this event. I would have liked to been here, been there as the two other speakers, but it's a long way to Boulder for a one-day meeting, so it's unfortunately not feasible. I will try to put CS into a perspective of a Danish Meteorological Institute where I'm working, and how we got into the consortium and the collaborations we've had with Elizabeth. And the picture you see, that's from Copenhagen. It's very rare we have sea ice there, so that's definitely not the motivation for doing the sea ice modeling. This will only be there for a day or two, so not even every year. But and I should also say that a lot of my collaborators at DMI, and one from Intel I've listed here, Jakob from Intel is there as he's been at DMI, but he's also worked a lot with me on the size things. So the real reason why DMI is doing sea ice modeling and observations, and unfortunately, it sometimes needs an accident for new security things or safety things to be started. And for Greenland or DMI, it was the Hans Hedtoft that went down. I'm not sure if they know. I think they think that it hit an iceberg, but sea ice and icebergs were sort of in the same category. So this event started the Greenlandic Ice Service as we know it today. In the beginning, they were flying to do reconnaissance, and I think the U.S. Navy is still doing that for the west, the coast of U.S. and North America. But it's an expensive way of doing it. So with all the new satellites coming up, DMI has moved to being completely reliant on satellite images, and the animation you see in the upper right corner is made by a colleague of mine at DTU. And you can really see all the dynamics that's going on, and an unusual opening in northwest of Greenland, where sea ice was moved away from the coast by winds, warm winds. But of course, it's February month, so it's gonna freeze over quickly. This is then translated into an ice chart, like you see in the lower right corner, and these are hand drawn on a daily basis. So these are really what we as modelers need to match in the quality in order to have the forecasts shown. That's of course, satellite images are nice, but they don't really provide a forecast. It's like the weather forecast. It's nice to know what it is today, but what's really nice important is what's going to happen tomorrow. Therefore, DMI had a boss. It was my previous boss at the Ocean and ice group, he said, okay. He went to a workshop and heard that HICOM was a really good ocean model. So he wanted us to try that. And that's of course very nice for ice-free oceans to have a good ocean model. HICOM at that time and still have a purely thermodynamic sea ice model. This was of course not good enough to do forecast. So we needed a sea ice model, and at that time, NRL, the Navy in US was working on including SEIS in HICOM, and we sort of hooked on to that as well. So we started our collaboration with the Navy and Florida State University at that time. This was also my entry into the sea ice modeling. And our first domain was a narrow strait domain. We wanted to see how did it work, how did things do, and as a little funny side story now that we're talking about implementing boundary conditions in an ice model, we did this in version 3.14 20 years ago, and I have no idea where that code is. Otherwise, it would have been obvious to put it into SEIS, but that's how it is. But it showed some similarities with what we could observe. We could have openings of polynyas forced by the wind. We could have a reasonable ice flow through the strait. So we all in all, we were happy with the first experiments. Then we moved on to a Pan-Arctic forecasting system. And that's an example for January 20, you can see on this one. Currently it's in 5 kilometer resolution. We started to engage with sea ice, the consortium, especially through the Canadians in the early 10s. And then and I think that was also through that I met Elizabeth for the first time in Ottawa some years ago. Pam Posey introduced me, and it's great to see that she will be talking later. DMI entered the Sea Ice Consortium in 2018. And in general, I don't think we've been as far as we are now without that, the community around and the development that has been done by other institutions. So we are really grateful for that. And the primary inputs has probably been on dynamical allocation from DMI and this EVP 1D solar. And I will talk a little bit more about that now. And this, as other things in SEIS, started with a hackathon, and that was a really good experience. We had Rob Alves visiting DMI, and then Tony Craig and Elizabeth was on the other end of the line when our workday met in the afternoon for Denmark and in the morning for US. So we started working this, and the publication came out last year. So it was a long time on the way. It was not because of that hackathon. It was just other things that did that. I'd like to dwell a little bit on this. So we all are provided with some compute resources at hand, and most models don't utilize the current hardware we have today. Sea ice is especially difficult in the sense that it has a lot of points where you have land ocean, which is of course static, active and non-active points, but you also have ice that changes by the season. And this means that your solvers will have a very large number of unused points, and that makes it difficult for the compiler to really use its optimizations tools. And often memory and bandwidth are bottlenecks. So we did some modification together with Jakob from Intel, who now moved from DMI to Intel, and Elizabeth and Tony. in order to improve the implementation of the VP solver. So we extracted it as a dynamical, as a unit, and did some experiments on that. Another thing that was clear was that the MPI exchange was a bottleneck. And all of these tests, as Jakob was at Intel, we tested on different Intel hardware. And just to say, without going into too much details, we could show that we could, by doing these changes to the code, we could now utilize the bandwidth of the different hardwares. And we achieved a factor of 5 on one core, and even more when we scaled up to one node. And we still have a task in getting a really good implementation on this into the size code. It is there, but there's still some bits and pieces that needs to be updated. And I think without having the good discussions with Tony and Elizabeth on how to integrate into size, we wouldn't have, it would still have been a desktop study. So we really appreciate that. And I think that was mostly what I have to say. So from the UMI, we first of all like to thank the consortium and the community. It's been, as Letty said in the beginning, it's an easy place to join. It's really well structured, and I think it's very rare that I say it's some really interesting monthly meetings. I'm not a big fan of meetings, but I think these are worthwhile attending. And then, of course, today, especially thanks to Elizabeth for engaging and the leadership and the hard work that makes CI such a good community model. I don't think that's feasible without having someone who steers it as well as she has done. And as well as Letty said, I haven't seen many models which are of the same standards. And I think that our IT persons at DMI think the same, which is really a good credit to get. So thank you.
Thanks, Tel. That was great. Any quick questions for Tel before we move on? But okay. So Fred, vous êtes ici?
Bonjour Dave.
Bonjour, ça va?
Oui, ça va et vous? Okay, I will try to find a way to share my screen.
It's a little button in the middle with the up arrow.
Does that work?
Yeah, and then if you could put it into presenter mode.
It's on my screen in presenter mode. I just wait a few seconds maybe for the latency, but otherwise I will, yeah. If it doesn't work, okay, so maybe I need to reshare again.
I have to mirror his talk. You have to mirror your talk, I guess, from your end.
Try again, see if I can share the correct screen. Oh, okay, maybe if I do that, is that?
There you go. C'est ça.
Ça marche.
Ça marche.
Okay. Bonjour tout le monde. Hi everybody. So yeah, sorry for not being with you. I hope you enjoy the party and the celebration. I'm going to present the perspective of CI modeling from the Environment Canada, or Environment Climate Change Canada, as it's called now. It's mostly work of my colleagues Jean-François Lemieux, Philippe Blanc, and Mathieu Plante, and others, mostly. But I'm here I'm the speaker. Yeah, I'm representing everybody today, I guess. So I guess I met Elizabeth in Victoria, British Columbia, in the early 2000 or mid 2000, because the Canadian Ice Service were inviting modelers to to show what we could do in terms of sea ice modeling. It was, I guess, a time where most climate models were still having very crude sea ice representation. So it was really the early start of sea ice modeling as we know it now at the time. And I guess Elizabeth was showing early representation of what we CIC was coming was going to be. And on my side, I was developing this sea ice model for unstructured grids, as you can see on the right. Then I was sidetracked by biogeochemistry in sea ice with IceAlgae for a few years, but then I entered Environment Canada and started doing work on an Arctic configuration called SeaEdge. And we, especially thanks to Jean-François, we became a member of a consortium in the mid 2010s, and we started to work with NEMO 3.1 and a couple to size 4. Jean-François was, of course, a very central person for doing the landfast ice parameterization that he developed, and we tested in that configuration. We also, I guess, defendant of the viscous plastic rheology. We think there's still some juice in this one that we can extract by extending it with tensile stress or playing with the ellipse ratio to represent better the ice drift and the ice deformation in the Arctic. We looked at impact of tides, and we explored a bit the form drag as well in one paper. And Philippe and Jean-François have been doing an implicit VP scheme that we still need to. Well, we would like to test more broadly. So that's just a few representation of what we've done. So the landfast ice, definitely that's that was the early work of Jean-François. Plus, I guess I should mention his work on EVP and how to make sure that the EVP can converge to a VP solution. On the bottom left, you have the work we've done with including tensile stress, and we're playing with the ellipse ratio, so make it more round and so that increase the shear, the resistance and shear. And you have on the right the landfast ice frequency. So red is almost a full year cover, and blue is lower frequency of appearance of landfast ice in the Arctic. So we see mostly this Canadian archipelago, where it's mostly the rheology doing the work, on the Siberian seas, where it's red, that would be more grinding due to keels touching the ground. So that's typically what we were getting in the SeaEdge configuration in terms of thickness field over the Arctic, and ISAT on the left, the model on the right, and the difference model minus ISAT at the bottom. So we were getting really reasonably happy with the thickness distribution we're getting in the Arctic. It was still, even though at some point we switched from rough rock representation of the ice resistance to Hebler, that helped in extending the zone of the high thickness region north of the Canadian archipelago and the Greenland into in the direction of the North Pole. But yeah, we're still fighting a bit with getting the reasonable gradient of ice thickness closer to the Canadian archipelago, I guess. In terms of so of course tuning the ice drag, improve the ice velocity. The last implementation of the of this is in the light green, which is the bias at the bottom is more or less neutral. This is the effect of tides, where if you analyze the ice velocity, do a tidal harmonic analysis of the ice velocity, you get pictures for the summer on the left. For M2, you have a main moon constituent, and or in the winter on the right. So you do see effect of landfast ice, for instance, region of very dark blue in the Siberian seas, or in some region of a Kenyan archipelago. But also the distribution of the velocity is quite different, which is of course quite interesting in general. So tide basically change with the presence of sea ice. The other thing I wanted to touch on was the recent migration we've done in operation from size 4 to size 6. So finally, size 6 is running now in operation. We're quite happy to do this change because of especially the dynamic allocation that the size 6 allowed versus size 4. So no more need to recompile the code anytime we wanted to change the distribution. The MPI distribution. There's of course a lot of new physics coming from size 6 versus size 4 that we haven't touched yet, except for the delta Eddington that we decided to implement in operation. I'm going to explain that in a moment. And of course, Jean-François's work, recent work on the RC rigor representation of ice velocity. So the issue though is that all the systems, we're running quite a few operational systems for the ocean, were impacted, and we had a lot of local change in the code for size 4, but we had to pull to size 6. So that was a daunting task. So the reason why we switched to Delta Eddington was basically because we found that you have a contingency score on the left for the proportional correct total sea ice in the Arctic, in Hudson Bay, actually in this case. Sorry, the blue is the previous version we had of the code, and the red was the new one. And so you want to be as close as possible to 1, which is at the top of a figure. And definitely we were actually degrading, where the red was below the blue during the summer. And we figured out that it was a previous migration. We found that problem, and previous we call it innovation cycle to be precise. We found that problem, and we figured that it's actually the switch from the coupled atmospheric model to an uncoupled atmospheric model that was changing the albedo of the snow and refraction of this shortwave at the base of the clouds and reflecting back to the ocean. So that's what I'm explaining here, I guess. We found that the uncoupled atmospheric cycle also was having too much shortwave compared to the mosaic data that's on the right. So the model is this orange curve, and the mosaic was the blue one. So so that was another argument anyway for switching to a scheme that could counter this effect of we had in the atmospheric uncoupled analysis. And so that's one of the reasons we switched to Delta Eddington, because we found that we could preserve the total volume of sea ice and the snow. So sea ice on the left and snow on the right with Delta Eddington. So the magenta curve at the top. So at least it was, in a way of counterbalancing this effect of the shortwave radiation being overestimated in the atmospheric model. And it did also lead to improved results in terms of this contingency table we had, so proportional correct total of sea ice. So red curve now is above, which is better. One thing we noticed though is during the ocean data simulation analysis cycle, which is every 7 days, we compare the thickness of this in this cycle versus the data obtained from mooring in the Beaufort Sea. And so the mooring is in black, and the model, there's two variation of a model, red and green. But basically, we found is that during the melting period, the analysis seems to have a shock due to the in ice thickness, due to the reset of the ice concentration to observe values. And so we'd like to explore that and make sure that the next version has less shock in terms of ice thickness when we simulate ice concentration. The other thing I want to touch on quickly is the probabilistic grounding that we implemented in the ice in the consortium code. So basically you have an ITD on the top left and representation of this ITD by a log distribution on the and in the middle and in black, and the same an Gaussian representation of the seabed depth in blue. So basically, the idea is that we're going to get grinding where these two distribution intersects. And just quickly, also what we found is that if we're using the older method for length size prioritization, which is on the top left map on the right panel, on the right figure, so the A panel, sorry, the extremes of this keel depth was much higher than that what we could get with obtain with that scheme. So we were over predicting, we think, the keel depth with the draft, the ice draft, basically with the previous scheme. So that was definitely, we saw that as an improvement. So in conclusion, we had a long and productive collaboration with consortium. We have the landfast style problematization I mentioned, the SIGRI, the probabilistic ice grounding, the multi-layer treatment of a basal growth, done by Mathieu. We really enjoy the regular meetings we have with consortium, and we think it helped the structure of the consortium activities. Elizabeth was definitely a great leader and caring person. We had also direct communication with some of the members of the consortium to do, for instance, intercomparison with the naval model or DMI for the coupling. And yes, definitely in operation, changing version of code is always a daunting task, and hopefully it was successfully implemented last year. And that's it for me. So it's a congratulations to Elizabeth, and enjoy your retirement.
Any quick questions for Fred? So I have one. You did not find a bug in Delta Eddington, is that right? You said
I
bug
didn't.
fix of Delta Eddington, so I just wanted to be. Anyway.
Sorry, I didn't get your comment, Dave. Can you try again?
You said bug fix of Delta Eddington. I thought you
Yes.
said you found a bug in the Delta Eddington.
No, yeah, no, we just took we did test
Okay.
with size 4 and size 6 with Delta Eddington, because there was a version available in size 4, but we figured that there was a correction done between size 4 and size 6, because definitely we were getting different response. And then we found out there was a bug fix done in size 6 for Delta Eddington.
Okay. Great. Thanks. All right. Well, we're going to take a 30-minute break or so. All right. No feedback?
All right.
Okay.
You'll
All right.
One question. Who's advancing the screen? You or me?
Oh, that will be you.
Me?
Yeah, that will be you, and you could use,
This thing?
clicker.
Okay.
Yeah.
That's great.
Or the arrows right here.
Because then I don't have to be like trapped behind this.
Yeah.
Yes.
Great. Okay, well, our next series of speakers, representing DOE primarily, and to kick us off, it'll be Dave Bader.
So hi, everybody. For those of you who don't know me, I'm not a sea ice modeler. I don't know what I am. Until tomorrow, I'm the lead PI for E3SM, but then I won't be. So just to give a little bit of background. Oops, clicker.
Oh, yeah, there it went. There was a
I gotta go back. So what I'm going to do is, this is not a technical talk. This is I've known Elizabeth since she was a postdoc. And this isn't even about just Elizabeth. It's about the incubator that created the Elizabeth Hunke we all know and love. So, so I've kind of put it in a bit of a story thing. It won't be that boring, but this is about the group at Los Alamos, how that got started, and how it turned into the anchor for the Department of Energy to get into climate model development. So as you read, you know, there was a parallel climate model, which was a new model that was built by a new concept at the time, a distributed center, right, with a new programming model of OpenMP and MPI on distributed memory supercomputers. So, and in this model, there was a new idea in the sea ice, elastic viscous plastic ice rheology, which was Elizabeth's postdoc work with John Dukowitz. So I want to tell you how she got here. So let's start at the beginning. So for those of you who have never met Bob Malone, unfortunately he passed away in 2020. He was great. I mean, he was a great person. He was a great friend, great leader, great scientist. You know, trained as a physicist by a Manhattan Project participant at Cornell, and he decided to go into climate modeling. So what I'm going to do is read from a document Bob prepared shortly after his retirement, I think 2004 or 5, sometime in there. When Los Alamos' contract changed, he made the smart move. He did not want to work for the new crowd. So he got out. But so this document is something that I have somewhere, and 5 terabytes of stuff I haven't sorted. So thanks to Phil for giving me his copy, which he did find. And I'm going to be reading some parts for that. So the seed for COSM was planted in 1979 when Bob Malone accepted a position in the T Division charged with building a climate modeling capability at Los Alamos. To learn about the state of climate modeling, Malone arranged to spend the summer of 1979 at NCAR. There he became involved in a very small project to develop a global atmospheric model based on spectral transform methods, which were new at the time, developed by the Australians. That's my added side note, for those of you who don't know where it came from. The project was led by Eric Pitcher and Ramanathan. Pitcher was a visitor, and Ramanathan was an NCAR staff radio transfer specialist. Ram had developed a new cloud and radio transfer scheme that was being installed in the model framework. Malone returned to NCAR for several months during each of the next 4 summers to work with Pitcher and others on documenting, validating, and applying the model. This model was adopted by NCAR in 1981 as the first version of CCM, and it eventually may have seen the tag CCM 0A was that model that Eric Fisher and crowd developed. The visit was useful in establishing helpful working relationships with Maurice Blackman, Warren Washington, Bert Sepner, Bob Chervin, and Steve Schneider. In the future, each of them, especially Warren, would influence in some way the direction of climate modeling at Los Alamos. Thus began a long-term collaboration between NCAR and Los Alamos that came to fruition under COSIM. So, skipping some of that. So this is the full picture, and thanks to Elizabeth for this, that she found it. We were struggling to find all the people at Los Alamos that I know. Nobody could find me a picture of Bob. So obviously, Bob retired before cell phones and selfies and all of these things, right? But this was a team that put Lionel on the map and started COSIM. And this was POP. How many of you know what POP is? Noted in the well-known earth science journal, Physica di Nonlinear Phenomena. So moving on, the success brought recognition and credibility to the Los Alamos project and laid a foundation which was important in creating a role for Los Alamos at the beginning of the Department of Energy's Computer Hardware, Advanced Mathematics, and Model Physics CHAMP program in 1990. CHAMP was a new computational initiative to bring massively parallel computing to climate modeling. The establishment of CHAMP opened the door for Los Alamos to build on its reputation and obtain stable long-term funding for DOE for the first time. Dave Bader, that would be me, then from Pacific Northwest National Laboratory, was appointed by Ari Petrinos at DOE to run the program. Bader then asked Malone to coordinate model development component of CHAMP while Bader ran the science team component. So, why do ocean modeling at Los Alamos? Malone's experience working on nuclear winter convinced him that it would be unprofitable to pursue work on atmospheric modeling. Not only was NCAR a dominant force, but there were an order of 20 atmospheric general circulation models in the international community. The situation was quite different in ocean modeling. There were only a handful of ocean GCMs, and most were derivatives of the original Cartesian coordinate model developed by Kirk Bryan in the late 60s. The small project had a better chance of having a significant impact on ocean modeling. There's an important difference between atmospheric and ocean modeling. Atmospheric models require a large set of people having the collective expertise to deal with all the resolved scale fluid dynamics and parameterization of sub-grid scale processes such as fluid turbulence, cloud formation, precipitation, cloud optical properties, rate transfer, aerosols, convective missing, and planetary boundary layer, and interactions of the atmosphere with the land and ocean surfaces. Water exists in vapor, liquid, and ice phases in the atmosphere and interacts with aerosols, the bane of my existence, which act as cloud condensation nuclei. Because there are many interactions like this that take place among parameterized processes, important experts are closely ensure consistent treatments. This makes it desirable, not essential, to have all these experts in-house, which is clearly only possible in a large facility dedicated to climate modeling. By comparison, ocean modeling is simple. The basic ingredient is fluid dynamics. The ice phase does occur, but only at the surface. It can be treated by a separate entity in sea ice. The main subgrid process in the ocean that must be parameterized is turbulence. Los Alamos had tremendous resources in fluid dynamics and turbulence to apply to ocean modeling, and a small team came to accomplish it. It is noteworthy that the first 6 people to join the ocean modeling effort were members of the fluids group in the theoretical division at Los Alamos. Moreover, massively parallel computers seem to be particularly well suited to global ocean models. Mesoscale eddies are about 10 times smaller than analogous eddies in the atmosphere. This means that 10 times as many grid points are required in both horizontal dimensions and because the time set must be reduced by a factor of 10 or so, a factor of 1,000 more computation. These requirements can well be met with massively parallel computers. Malone approached Sepner and Chervin about attaining a copy of their ocean GCM as a starting point, which they generously provided. Now, this is one of the first examples of what we now call refactoring. That wasn't a term back then. But Bob, Rick, and John basically took Sepner's model tore it apart, and recoded it for the connection machine. So, and in doing so, got rid of a lot of bad code, a lot of things in there, plus structured it so it could run on the computers. I'm talking a little bit about POP. Rick and John Dukowitz soon joined the effort to develop POP. With PhDs in nuclear physics and aerophysics, respectively, they were immune to, this is the way we have always done it market, which, side comment here, I found particularly true among oceanographers. So, which Bert Sepner gave me lots of stories on the way he had to fight the way oceanographers did things, but that's for another day. I don't want to upset any of my NCAR colleagues who are oceanographers. It completely reformulated the barotropic mode of the model and replaced algorithms with new ones that would parallelize efficiently. So, what was remarkable about these changes simultaneously improved physical realism as well as computational efficiency. The new code was dubbed the Parallel Ocean Model, POP, by Smith during a visit to GFDL as a play on GFDL's MOM model, Modular Ocean Model. In 1992, team received a Los Alamos Distinguished Performance Award. In 94, the team won the Computer World Smithsonian Award in the science category. The first release of POP took place in 1994. So let's go to my next. So, we want to talk a little bit about sea ice. A little bit more background of the building of COSM. So, 1993, Matt Moultrie became the first member of the team to hold a PhD in oceanography. All this work was done without an oceanographer. He had grown up in Los Alamos, had been an undergraduate student working in T3. He moved into a postdoc position. Moultrie became interested in the POP work and began to work with Sepner's 1976 thermodynamics only sea ice model when in 1994, Elizabeth Unkey, our second postdoc, joined COSM to work on sea ice modeling. This allowed Moultrie to move to POP work, a model verification and validation. He and Rick Smith were the first to use POP at 10th of a degree. Unkey teamed up with Dukowitz and they repeated the POP experience by thoroughly rethinking approaches to sea ice modeling. They developed a new EVP rheology and dynamic scheme that addressed the most pressing shortcomings of sea ice models. Traditionally, sea ice stresses were modeled by a viscous plastic rheology that resembles that of a highly non-linear viscous fluid whose effective viscosity becomes singular at low strain rates. To make such a model tractable was to hold viscosity constant each time step. So physically, the singular low strain does not exist because sea ice responds elastically in this regime and resembles a rigid body. Unkey and Dukowitz introduced a simple elastic regularization that mimicked the physical response, but was primarily intended to improve the numerical behavior. So, and we have the birth of Elizabeth Unkey in sea ice. So with that, I paying tribute to the founders of the COSM program. I have this list from this table. You can see Phil, Matt, and Elizabeth, who were there at the beginning and helped establish Los Alamos, and this gave us credibility as an agency and as DOE laboratories to pursue climate modeling. And I have one more incidental story to tell. Y'all know I'm from Lawrence Livermore, right? When I was running the CHAMP program, I shut them out intentionally because they weren't going to do it right. So, twist of fate, I ended up there, but yeah, that was interesting personal history that I guess has a sense of humor, right? I don't know. Anyway, so thank you everybody, and thanks to letting me talk about something that's not sea ice, but I think is incredibly important. And, you know, when I think of Elizabeth, this is what I think about. So thank you very much.
Thanks, Dave. That was great. Matt?
Thank you. I'm really glad you pointed out the small but not insignificant role I played in getting out of Elizabeth's way so that you could do the sea ice model. There's no way I would have been able to take it to the extent that you did. So you did such a fantastic job. I feel really glad that I was smart enough to get out of your way.
Excellent. All right, Andrew Roberts.
People hear me?
That's good.
Got the slides up. Right.
All right.
Okay. Oh, goody. Well, you've all heard of the sea ice index, and there's lots of indices in everything we do. But I realized when I look back at my career over the last 20 years, there's one index that's missing. It's this ephemeral contour running through sea ice modeling, and that's the Hunke index. And the Hunke index is binary. It's 0 or 1. And there's another thing that's very common, as you'll notice here, is the word coupling. And that's really been the story of my career. But you'll also notice that of all the things I'm about to show in a very quick tour, most of those involve Elizabeth Hunke in one way or another. And most of those involve many people in this room. So you as a fresh postdoc at University of Alaska, I had a postdoc with Bill Hibbler, and there were these new exciting results. GPS had just become this great thing, starting with German observations in the late 90s in the Weddell Sea. And it became apparent that there was lots of interesting information in sea ice drift that should have been there based on physics, but we'd never been able to observe. And all of a sudden we could. We had GPS observations, and we noticed there was a huge inertial signal. Does this point to work? No, huge inertial signal with inertial oscillations. And on top of that, there was all these interesting ideas about whether there could be amplification with tides. So on the right-hand side is the inertial period for the Arctic, and you'll see that there's places where that's coincidence with certain tidal periods, the S2 and the M2 tides. And this is the only place on Earth where this happens, except for a very slender margin of the Weddell Sea. So it opened up all sorts of interesting ideas that were exciting to me. And so I pursued a postdoc with Bill Hibbler for tidal modeling of the Arctic. And so we built a separate standalone toy barotropic tidal model. It wasn't that much for a toy model. It had a resolution of 7 kilometers. And we were able to model tides using work that was initially done by Andrei Poshetinsky. And one of the things that was different in what we did was, instead of modeling sea ice as a separate momentum equation, we combined the ice and the ocean together on this equation on the right-hand side. And you'll notice that the only term that's explicit there that involves sea ice is the internal stress term on the very right-hand side. And this opened up all sorts of interesting ideas of whether we were really modeling sea ice correctly by separating things out between a coupler, between the ocean and the sea ice in particular. And somebody popped up in my email one day. I'd heard a lot about Elizabeth Hunke. I was desperately frightened of her because she had this amazing publication record. But I had a very, very kind email. I had just had quite a personal struggle with cancer. And the email acknowledged that and said, I understand you haven't been well. And it's something that really struck me at the time. I was just a nobody sitting in Alaska, and I was recovering from this. And it also gave me a lot of hope, and that experience actually freed me up to do all sorts of interesting things in life that I probably wouldn't have done had I not had that experience of the bit of the struggle. But this is where Elizabeth Hunke entered my life. What's going on with embedding? Everybody's talking about embedding sea ice in models. Do we need to do it? What's the impact? So what the point here was, this is really Bill Hibbler's point, was that there was no pressure force of sea ice on top of the ocean. And so this was all fine for virtual fluxes, but in reality, you can't all of a sudden take mass out of an ocean, which wasn't happening with virtual fluxes, but it does if you have a mass and a heat and a salt conserving ocean, the way we're going now, everybody in this room, for coupling. And so you can't do what's on the left-hand side anymore. And so we needed to come up with a better way of having the pressure force of sea ice on the ocean. But it turns out, this is the interesting thing that a lot of people miss, is that equation on the right includes all of that, but it's not very clear as to how pressure ends up with that result. But it does if you derive the equations. And the important point here is this allows easy transmission of the curl of wind stress into the deep ocean. It's effortless. And it's a problem we still have in coupled models by coupling sea ice to ocean through a coupler. We can only get a certain way to solving this problem. So this is something we are still working on 20 years after Elizabeth sent me this initial email. And then our involvement became even more because we realized that we didn't have the tools we needed to even begin to explore this sort of thing. I became involved in putting together a science plan for a regional Earth system model just of the Arctic called RASM. And it was primarily for National Science Foundation, but DOE ended up funding this. And as part of that, we got stuck into the coupler. We took CSM, we regionalized, we put WRF in, and we got stuck into the coupler with many thanks to Tony Craig in particular, and realized there was all sorts of things going on the coupler that we hadn't expected. And there were time lags and all sorts of problems that could cause a model to crash. So we put together this regional Arctic system model, and this is where Wisław Masłowski in the room led this effort. It was tremendously useful to me because we had a nice little laboratory to explore things. And what we discovered is that there was this rich drift profile, drift spectra for sea ice that we were completely missing in models. And so I came here and spent some time and talked with Marika and Dave, and we ended up running CSM and making changes to the coupler, and were able to correct this problem of there was no inertial signal in sea ice drift, and now there is in CSM and E3SM and RASM. As part of that work, we found ourselves continually updating SEIS, and SEIS became very, very important to me. And I found myself working more closely with Elizabeth more and more, to the point that the SEIS consortium formed. And I remember the first meeting where we all agreed that we needed the SEIS consortium. So here are some of the initial models involved: SEIS-6 from Elizabeth, GOFS from the Navy, RASM from many institutions, Naval Postgraduate School included, CSM, and the Canadian model. And we realized we needed some sort of quality control. And at the time, this wasn't something everyone was talking about, but we derived a method to be able to control very quickly, just run for 5 years to determine if changes in a sea ice code were climate changing. So this might seem like a trivial detail, but it ends up being really important for understanding whether non-bit for bit changes really affect your larger coupled model, they're very expensive to run. As part of that development, we separated out I should say Elizabeth separated out the royal we. I helped get this into other models, separated out the column physics from the dynamical core, which then freed up more applications of that work. So right now I'm working on a project called E3SM that Dave just mentioned, and we don't use SEIS. We use a different die core. It's unstructured on the left-hand side, but we use IcePack throughout. And all of that column physics is really important. So I'd like to stress how fundamental this is. There's only very few experts in the world that are specialists in Snicker or in melt ponds and so forth. And this is a really important way of pooling our resources. And I think it's proven to be incredibly powerful. So that's what we do now in E3SM. We use IcePack, and we've just got this up and running, and the results are really terrific, I think. So one of the points of E3SM is it's focused on computing, energy exascalar system model. And we are using unstructured meshes that really do a great job of refining coastlines. And we're increasingly trying to improve our representation of sea ice along coastlines. And just in this version 3, we now have this up and running. So it's been a long story to get here, but this is where we're at. We're now making a couple of predictions, like many people in this room, which I think is the ultimate purpose of science, to be able to make predictions. They don't have to be about the future. They can be predicting things that we didn't expect to find in observations. And perhaps on a difficult note, we are predicting that this decade we will be ice-free in the Arctic. We have a few ensemble members going ice-free up till now, so the probability is still low, but that's where we're at. Ultimately, everything we do in this room is important for making predictions. So what about the predictions for not the future? And this is the only part that's not coupled yet. And this is outstanding work between Elizabeth and me. And this received a green score, not a blue score, you'll note, because Elizabeth and I worked really, really closely on this, working out that, in fact, the way we represent morphology in sea ice models is deficient in one sense, that if you don't include big blocks of ridged ice, you end up with very, very different answers for the deformation characteristics of sea ice. Elizabeth and I worked on this for years together, and it was probably my most extensive work. It was really what I intended to do for my PhD, and I didn't have the skills nor the understanding to do it then. But what it's showing is that if you include macroporosity, the color bar on the right-hand side, in ridges, you're able to match the shapes of ridges, the average shape, which is this cusp shape in a grid cell, really, really closely with upward-looking sonar, with side scan sonar observations. And this is the work that Elizabeth in her retirement has hopefully interested in continuing on with me. Because I'm not dropping it. I think this is a really good thing to do. So on that note, I will say that the most important thing that Elizabeth has shared with me is her kindness. And it's made me appreciate that as colleagues, it's really important to be kind with one another, because it opens a whole lot of scope for discussing interesting ideas if people feel comfortable in meetings, or if they just feel at ease. Often some tremendous creativity can come of that. And at least for me, Elizabeth helped foster my career a great deal. And she's bringing up my daughter as well, who's cleaning Elizabeth's plane here. And one other thing that I will note on this, it's very telling. Young children have a great judge of character. Within a day of my daughter at this age meeting Elizabeth, my one memory is of her giving her big hugs all the time and being wrapped around Elizabeth's legs. So I'll leave that thought with you.
And then next up, we have Nicole Jeffrey, and I will preface by saying I apologize for your title. I made that up, but we'll see if you change that. Yeah, absolutely. I think, is the roof mic on?
Just one note, you are using IcePack, but the thing that you're also using is EVP, which was the very first thing that I did in Sea Ice. Well, after recoding Sempner's zero layer model from Fortran 4 to Fortran 77. But, you know, I never imagined that EVP would last more than, 10 years. I mean, what's the lifetime of a code? And it got completely recoded for the non-uniform grid. but it's still the basic algorithm that's being used in E3SM. And to me, that is really gratifying, rewarding. So. Thank you.
All right, well, we'll change themes a little bit here with Nicole's talk, but take it away.
Yeah, and can you hear me okay with this mic? So yes, I did not pick this title. But, and you know, Dave did ask us early to send titles, and I didn't, but when I saw it, I thought, you know, this is great. I do have to give a talk that says, if I had one suggestion, it would be this. At the bottom, I have a lot of symbols here, and I'm forgetting things. These critters in sea ice, this is how I met Elizabeth, and this has been really the history of my experience working with Elizabeth. So it's actually a very fitting title. And there have been a lot of projects and a lot of interactions, and some of them, I'm not going to always point them out, but just to let you know, there's a lot of people that have contributed here. Okay, so when I started, so I didn't know Elizabeth as a postdoc, but she's known me since I was a postdoc. And when I started, I knew really next to nothing about sea ice, and that's not an exaggeration. I came from doing a PhD in oceanography with a biogeochemical model, and Matt and Scott and Elizabeth were seeing algae in the sea ice. And, you know, they found out I had done this, and so they brought me in to this meeting. And I kind of remember some of the early conversations we had, because this first picture here from Richard Cullerther, I think it came through Marika, maybe, to Elizabeth, right? To me, and I've been using it in talks for the last, 15 years. And the upper one you've already seen as well. That's from the Arctic, and I've been using that. But when I first had that meeting, and Elizabeth was telling me, sea ice, it's from salty water. It's not going to be like an ice cube that you have when you melt it from, where you freeze it from fresh ice. And, it was very inspiring. I went home and I made these ice cubes out of salt water right away. And, reflecting on my experience with Elizabeth, she's been my teacher and mentor all these years. What makes her so good? And a lot of people, okay, we've been talking about you. I'm going to admit it. A lot of people have said, well, it's her kindness, it's her patience and humility, and all those things are true. But for me, I think it's her curiosity. It's her relentless curiosity about all things ice, and that rubs off, I think. So this work I'm going to show you is going to be a little history, my narrow history of trying to get ice algae into sea ice from a modeling perspective. One of the first things that we did was focus on that particular picture. I said, okay, that's going to be easy to do. It's a layer just at the bottom. We can take our ocean biogeochemistry, we can tack it onto our really cool sea ice model, and just get that bottom habitat that we're looking at. And this was work led by UAF, involved a lot of people, and we got a simulation going, a forced simulation, and the result was about 10 teragrams of carbon per year, which is, at the low end, but it's right in with observations. And that's sort of the first thing we did. But we were sort of excited about the whole problem. I'll go back to this one. There's algae in the internal habitats. Within the brine channels, there are surface habitats. We wanted to get at everything so we could get at both pictures. And so this picture that I think a lot of people have seen as well is an X-ray tomography from Ken Golden. Ken Golden came to visit, and he found if you could figure out what the porosity is, you could determine what the permeability is. You can see that when it's really cold, some of those brine channels are not connected, and so it's not going to be permeable. And so he had this idea of how to get at the permeability. And when we thought about how sea ice forms, you know, that brine at the top, when it's colder, is going to be denser. And so you have some gravity, drainage overturning. And surely, even if we don't have salinity yet, we could derive a passive tracer transport mechanism for the sea ice. And that's the first work we did with Elizabeth and I. And we tested a couple different kinds of parameterizations. The mixing length diffusivity is the one that had the right behavior. You would get larger fluxes with better growing sea ice, rather than just trying to crank up a molecular diffusivity. But we still didn't have salinity in sea ice. We still couldn't evolve the porosity without forcing. And Steve Ackley would tell us there's these gap layers up inside the Antarctic sea ice. And so then we went back and said, okay, let's take the bits of Lipscomb scheme. Let's take that mixing length diffusivity, and now we'll just evolve the salinity. We won't worry so much about coupling it too closely with the temperature or changing the scheme itself. And that's what we did here. And this picture is really like a single location in the Southern Ocean. And you're looking at a forced simulation where the ice is growing. So that's, you can see the thickness of the ice growing at depth. You can see snow piling on top. And the top one shows the salinity. So when the snow gets higher, it floods, and we see salinity at the top. And then if you look at the bottom, when it's starting to melt, you see that yellow. You sort of get a bit of a gap layer. So that was sort of the first thing we did, where we had this Z salinity model that we put in. At the same time, Elizabeth is working with Adrian and Cecilia, and they are working on the multi-layer thermodynamics. And in this case, that couples the salinity and the brine motion with the temperature equation, and has a far more stable and superior numeric scheme. And so this is the one that we use now, and she was able to get this model in. Okay, so yay. Now we have salinity. You know, we should be able to take that biogeochemistry and vertically resolve it. We have the processes we need. And version 1, that's exactly what we did. We added the BGC. It was called the Los Alamos sea ice model. It's SICE at the time. Very exciting times. And then we did version 2 because it was time to rewrite the code for really good reasons. We needed to columnize it. And we did. We columnized both the physics and the BGC. And that eventually becomes IcePack. We did do a little bit of science in there. We managed to put in dimethyl sulfide and look at the interactions during that time. And then MPAS came. So we did a version 3. We needed to rewrite the code again for MPAS sea ice. And we did. And finally, we had version 1 of E3SM. We had this vertically resolved code running. This was one of our first simulations. At the top, you're looking at Arctic primary production. And I do want to point out the value we got, 7.5 teragrams of carbon, which is a little worse than the skeletal layer model we had at the very beginning, okay? It's dropping down below observations. But it was very novel at the time, so we were able to get this published. But certainly we did have biases. The Southern Ocean is better. I think at the time, even when I wrote this paper, I entirely blamed the ocean. The ocean had these biases, and people accepted that. But other people in the community are still doing work with sea ice algae. And papers were coming out saying, listen, there's a biofilm in there. Can't just have a biogeochemistry with tracers that move like salinity, because the biology forms a biofilm and it causes things to adhere inside the ice. So we had to think a little bit about this. We had to update things. We added a virtual biofilm inside the ice. We could stick things in. Nitrate doesn't always evolve like salinity. People were taking cores and finding that the bulk nitrate in the sea ice was greater than what was going on in the ocean. I said, that's not possible in the model. Yeah, because I didn't include a biofilm. I didn't include nitrification. So there were some processes that we had to include. And so we did that. And here we are at the kind of latest and the greatest version is the E3SM version. This is sort of hot off the presses, but if you compare what we had in the Arctic, 7.5, we're now up at 22 teragrams of carbon per year. And that is really consistent with observations. The high end is because sometimes you get really high spikes in primary production, but other estimates are right around where we are. So it looks like we're done, but of course we're not done. This is just sort of the beginning. So Andrew gave, a bit of a description about the work he's doing with macroporosity with Elizabeth. That's incredibly important. Once you have macroporosity, now we can get at the ridges and the ridged communities, which are like, people go out and measure and they go, this is the place where a lot of the algae is sitting. So we're sort of in a position we could, as soon as we have that, we can now have ridged communities. Algal math. Okay, if you go and look at the sea ice, often you see this. This is a single-celled organism with a chain. And again, it's similar to the skeletal layer, but it's not. It's below, and it has access to the ocean itself. But not something that we couldn't do or put in this model, because that's responsible for a lot of high primary production. This one we've been talking about for ages. There's gas exchange between the sea ice and the atmosphere. Some of this is biogeochemistry, some of it is just chemistry, but there are things that we could add that have interesting implications. There's the bromine and ozone interactions. There's the carbonate chemistry within inside the ice and CO2 fluxes. So that would be excellent for people to do. Here's another one. This is actually a dust, I don't know why it says Boulder. Okay. That's just because of this. This is actually in Perth. Okay. This is not Boulder. This is in Perth. That's a dust storm. A dust storm coming off. We've recently just included dust and iron contributions into the sea ice that interact with the biogeochemistry and interact with the ocean. So that's a new piece that we're also looking at. And finally, the last one I have is the sediments in sea ice. We just put, this is kind of a test where I had quickly put sediments inside the ice coming from the river sources, but these are also picked up from coastal erosion. They're picked up from the bottom of the ocean, especially when you have landfast ice. Frazzle ice picks it up, and it helped us think about frazzle ice to do this process as well. So, and they have biogenic material that's going to interact with the sea ice. So there's lots of things that I'd love to see this work go. This code is an E3SM version 3, but it's also an ice pack right now. As of August 2024, it's available to the community as well. Okay, I have one kind of last thing. First, I hope that you can see all that work. I feel like it's a ton of work, but Elizabeth was absolutely involved in every aspect of it. And for her, it's like this small part of the breadth of her work. Thank you for being there for all that work. But I also wanted to add something that maybe people don't know about Elizabeth. And so I thought of expanding your horizons. So maybe you don't know, but Elizabeth used to volunteer to do a workshop, expanding your horizons, for girls, only girls, which is okay. And to teach them and get them excited about science. And she and I, eventually she asked me to join her, and we do this experiment together. So what I did is I recreated the experiment with my little helper here. So I'm gonna click, okay. So you can see, we just did it in my kitchen last weekend. Okay, so the experiment is you take fresh water on one side, salty water on the other side, you add some ice cubes, and then you put some food coloring. We'll let them catch up to me. And then you ask them, okay, which is the fresh water, which is the salt water, and which one will melt faster? Now, my 8-year-old guessed it right. And I know which one. So I think everybody in this room can probably guess that one is behaving quite differently than the other one. When we first did this experiment together, a couple of times, you have to prepare the salt water in advance. And I left it in my car. And I thought, oh, I'm going to mess up the experiment because it's warm. And we went in and did the experiment. And, you know, sure enough, the salt water, which is, of course, the red, melted slower, even though it was warm, because of the stratification. And if you touched it, you could feel the heat trapped below. And it ended up being really cool because the kids would come up and touch it. You see, that's what's happening. We're trapping this heat down below, whereas the other one just fixes up. So thinking about this experiment, I wonder, you know, how many girls you have inspired with these ice cubes. I'm not the only one.
That was so awesome. Are there questions, Dave? Yeah.
The cowboy shirt, you're in Bronco country.
My son,
Yeah, it's
he lives too close to Texas. We don't have, yeah.
you gotta fix this.
So, anyway, next up we have Erin Thomas. She's going to talk also about some wave ice interaction, but I actually wanted to ask about those algal mats. Maltrud, did you have anything to do with that? I mean, never. Anyway.
No comment.
So, hey, just click your slides.
Yep,
and-
sounds good.
Yep.
All right, so Dave said I was going to be talking about some wave ice stuff. There'll be a little bit of that. I had a really hard time coming up with a title. And so my first slide is in fact blank, and I will go through my thought process for how I came up with the title. But in case you don't know me, I'm Erin Thomas. I am at Los Alamos National Lab. I have only been there for about 3 years now. So I have no qualifications to talk about stories of knowing Elizabeth longest or knowing Elizabeth the best. And so, whoops, nope.
Oh, it was just delayed.
Oh, it's delayed. Anyway, so I cannot title anything about history with Elizabeth because we've only known each other for 3 years now. However, we do have a bit of a unique story. And so my presentation is going to be stories of propagation, Elizabeth and Earth system modeling. And I will go through various definitions of propagation and how they apply to our story. And so one definition of propagation is the transmission of something in a particular direction or through a medium. And so you can see how this is easily applicable to Earth system modeling, especially the work that me and Elizabeth have done with wave sea ice interactions. And so the last 3 years, I have been working with Elizabeth to implement wave sea ice interactions into our Earth system model E3SM. And so very recently, as of like last week, we have a fully coupled system with a wave component, and we are simulating the wave sea ice interactions. But before I get to those fun results, we only have one test year done so far. But this is the general setup that we've been working on. This is really the only science part of my presentation. But really it is thanks to IcePack and the default column physics within MPAS Sea Ice, our ice component, which contains the flow size distribution. And then some hard work implementing WaveWatch 3 as our wave component that we can really simulate the wave sea ice interactions that we're doing. So we are able to estimate what the flow size distribution is due to the wave breakup. And so here are some very hot off the press as of last week. So this is a fully coupled E3SM version 3 simulation with fully active flow size distribution and fully active WaveWatch 3. We have an example from the Antarctic here. So March and September on the bottom, the left-hand column is the sea ice fraction. In the middle, we are looking at the significant wave height. And then on the far right-hand side, we have the average flow size diameter. And so we are starting to see some pretty interesting interactions, especially on the edge of the sea ice, where the impact of waves is most important. Just keep in mind, this is a 1-year simulation and we need a bit more spin up before the results are actually meaningful. But we are seeing some really fun scientific results. And so I'm really excited for the future and what we can do with some of this coupling work. And so that's actually it for my science focus. Propagation has several other meanings. And so I moved halfway across the world to take this position at Los Alamos. And I'm an avid houseplant grower. And when Elizabeth found this out, she is also an avid gardener, and she donated many houseplant cuttings from her own houseplants to me. And so I have several growing trees in my apartment that are directly propagated off of Elizabeth's own houseplants. And so the second definition of propagation for Elizabeth and my story is the increase in numbers of a specimen by natural process, so the cuttings of houseplants. However, there's some other related topics to this. And so the second thing she propagated to me, which, you know, the first thing, the houseplants, was very consciously done. She gave me all of her cuttings. The second thing I think she unconsciously propagated to me, and this was really her attitude towards science and her mentorship towards an early career scientist in particular. And so she really donated to me her humble attitude. The very first month of my position at Los Alamos, Elizabeth took a crash course with me to learn how to run E3SM. And I remember being just so impressed that one of the world's most renowned sea ice scientists is going to sit down with an early career scientist who has no idea what's going on and learn how to run E3SM, or maybe I should say, learn how to crash E3SM. And so we spent several weeks debugging just standard E3SM runs together. And that was just incredibly valuable, Elizabeth. So thanks. And so really, like the propagated houseplants that are now taking over my office and my apartment that directly come from Elizabeth's houseplants, you know, really just widely spreading the ideas and theories and her attitude and curiosity towards science and mentorship of other early career scientists is something I hope to propagate forward as well. So thank you, Elizabeth.
Oh, thanks so much. Yeah, that was great. Yeah, go ahead.
Plants, not Marika has some very special plants, specifically a begonia, and I was maybe that should be propagated onto other communities. I don't know what the rules are about propagating said begonia, but
Yeah. Should I explain what the begonia is?
Sure.
So we refer to them as Einstein Manabi begonias because they were propagated from a begonia that Einstein owned. And so the story that I've been told is that Einstein gave a cutting of his begonia to a secretary. That secretary gave a cutting of that to Suki Manabi. Suki Manabi is a close friend of my parents because my father was an oceanographer. So I know this story is true, that Suki gave my father a cutting. And now these begonias have spread around quite a bit. So I have 3 or 4 of them. Several people have gotten them as gifts when they've received tenure and things like that. So Jen Kay has one of these begonias now. She's been spreading them around too. So I have no idea how many people now have these begonias. I should maybe give you guys one to bring back home. I would love that.
Sorry. So Jerry, hopefully you're there. Oh, Jerry, you're muted. No, we're still not hearing you. Oh, wait. Do I have the order wrong? I thought it was Jerry first. Okay. Is it? Huh. All right. Do you have any suggestions there for him from his side?
Jerry, unmute yourself.
Yeah. Okay. Okay. Do you see the little microphone at the bottom of your screen? Is there an arrow through that? Or maybe you don't have the device pointed out correctly. Try hitting the space bar. No, still, I'm not sure what's going on at his end. Maybe we'll switch the order up. Is that okay, Jerry, if I go ahead with Dave? Thumbs up. Okay. Well, he can't argue with me, so. So we're going to switch the order up. We're going to go with Dave Livermore. Hopefully you're unmuted.
Can you hear me?
Yes, we can.
Okay.
And if you can share your presentation.
Let's see, here's the share, I think.
Yeah.
Let's see if I can find it. Would like to. All right, so now I have to find out how to get the screen. Yeah, I'm not sure what that is. All right.
We might have to pull it up for you.
Yeah, why don't you do that?
Okay. Okay. That'd be great. Thanks, Paul. And then I can switch the slides for you here. Just let me know.
Yeah, I'll just say next slide.
Yep. Okay, we can see it. You can go ahead.
Next slide. Okay, so first some words about Elizabeth. I was basically acting as a co-advisor for her at Arizona many years ago. Mac Hyman and I worked with her advisor, Joe Zander, to help her shape her dissertation more in the direction that she wanted it to go. And knowing her, I saw that she faced many challenges, both professional and personal. And if she's willing to talk about it, she'll even mention some aviation ones at dinner tonight. But she came out of the experience, as I say here, stronger, and that was visible. During her dissertation, you saw her scientific initiative that now all of you know she's demonstrated throughout her career. And it's been a joy to follow from afar this career. I know people who've used sea ice or whatever you call it, but I also was on AthCAC for a while and got high-level briefings. So this was very interesting. I should relate, though, that it's shocking we're celebrating this milestone in her career now. It scares me when I see my students retiring. So all the best for what comes next, Elizabeth. Yeah. And now let's go to the next slide. So I want to talk about the origins of fluid dynamics. I don't work in sea ice, but all of you work with fluids. And so I thought I'd talk about the three major contributions to fluid dynamics. And the first two you might recognize, and the third name may shock some of you, but it's actually the one that you use the most. And so let's quickly go through them so you have an idea what I'm talking about. So next slide. So of course, Euler was the beginning of it all. What's amazing about Euler's theory is it's the first nonlinear dynamical PDE theory. It just comes out of nowhere almost. There was preparatory work, but it wasn't PDE by Daniel Bernoulli. And something we know, we don't even think about it now, this is the first time you see pressure presented as a function of position and time. Before that, pressure was just a number that you would measure pressure inside a vessel, something like that. So it's a huge paradigm shift, the notion of pressure as a field. He derives these two equations you see there. You recognize the continuity equation, you recognize the motion equation, and if you count variables, he has one more variable unknown as unknown, so he needs to close the thing somehow. So next slide. And as you know, for incompressible fluids, which he called incompressible fluids and identified as liquids, he added the famous incompressibility constraint. And that closes the equations nicely. For compressible fluids, he was at loose ends. I mean, he knew that the pressure had to be a function of density and temperature. There were some, at the time, famous experiments by Amintons who had suggested, in fact, that pressure over density depended linearly on temperature. And these are well before the dates that you often learn about in physics books, but it was known to Euler, this work. And what we tend to know is that Gay-Lussac codified this by doing a whole variety of gases in the early 1800s, but this was already well after Euler. He did talk about the case where you drop the temperature dependence, and that's what we now call barotropic. Next. So the next big innovation is, of course, Navier. And Navier was motivated by Fourier's work on heat and was working also on elasticity. And he used the intuition from his elasticity work to come up with what we now call the Navier-Stokes equation. Stokes was nowhere to be seen at this stage. He introduces a parameter, the viscosity, and he also derives slip boundary conditions, which we now call often Navier slip boundary conditions, for the tangential component of U. Of course, the normal component is impervious, is zero. Okay, now his derivation employed a molecular model for the fluid, which was not widely accepted at the time. People really thought of fluids and gases as continua. And this created some problems for the acceptance of the theory. Next slide. And Poisson comes along and extends, if you wish, Navier's theory to the compressible case. He sticks with barotropic fluid model. The significance is, and this was partly motivated by work on elasticity by Cauchy and Cauchy, is he introduced now two potential viscosity coefficients, the mu and the lambda there in equation 5c, and he introduces, well, no, Cauchy actually introduced the stress tensor as the object of force. He put the stress tensor on the right-hand side of the equation because this is the famous ma equals F, the force of Newton. Now, Laplace had a theory of sound that wasn't too old at the time, and Laplace suggested what we would now call a gamma law equation of state, a suggestion that actually originally went back to Lagrange, but there it was. Laplace actually nailed it. The gamma, of course, was the ratio of specific heats, and but they had all kinds of trouble actually measuring those back then. So next slide. Now you wonder where Stokes comes into it, and here he comes. First, we need Saint-Venant, who actually made everyone happy by publishing the first derivation based on a continuum model of these equations, including the Poisson constitutive relation we just saw. Stokes, in his first paper on the subject, essentially gives the same derivation, a fact he embarrassingly acknowledged in a note the following year. He did two other things in his first paper. He insisted that no slip boundary conditions were correct. And it's not a bad approximation, but as history showed, it's not correct. And he developed a theory of how viscosity attenuates sound using the Poisson model we just saw. And that, of course, isn't correct because it doesn't have an energy equation. So why does Stokes get his name attached to the paper? Well, that's his to the equations. It's actually his next paper. What he did was use the equations to describe the drag on a ball, what we call Stokes flow approximation now, and actually went back and compared it with the predictions of the theory with real experiments that have been carried out over the previous decades, and showed that the PDE actually agrees, led to predictions which agreed with experiments, which surprised many people. And this was really the beginning of the acceptance of the Navier-Stokes equations. Next slide. Now, where's Maxwell coming in? Holy cow. When I grew up in kindergarten, they never taught me that Maxwell had anything to do with fluid dynamics. And I learned otherwise. So they were still trying to figure out what heat was. Heat was viewed as some strange object called caloric, massless stuff floating around. It wasn't viewed as kinetic energy of small motions of atoms or molecules. However, Clausius in the 50s was proposing exactly that. So kinetic theory of heat is exactly the theory that heat is really kinetic energy on a small scale. And so Maxwell was inspired by this work of Clausius, but not to accept the theory, but to try and refute it. And what Maxwell understood is, first he was able to derive this famous Maxwellian distribution. And he took this concept of mean free path that Clausius had introduced and was able to make a mathematical argument that if this was the case, then viscosity would only depend on the temperature as the square root of the temperature and not upon the density. And he thought this was surely wrong, and experiments would show it, and it would torpedo the atomic or the kinetic theory of heat. However, he couldn't find such experiments, and with the help of his wife, he actually did them. And he came away to his amazement to see it didn't depend on the density, but it didn't depend on the square root of the temperature either. It depended on the temperature, or seemed to be almost the temperature. These experiments convinced him that Clausius may be right. However, the fact that viscosity depended linearly on the temperature told him the hard sphere model that Clausius had used can't possibly be right. But now being optimistic, Clausius also had this notion of a gamma law gas that he thought this has to do with specific heats that he thought would be helpful. Next slide. And now in one of the most remarkable papers in physics, probably the most remarkable paper in physics from the 19th century, in one paper he derives essentially the Boltzmann equation for gas molecules, whose interactions are dominated by binary collisions with an inverse power potential. From it, he derives the full Euler system. What you may have noticed is Euler's systems I've written so far don't have an energy equation. Well, here it comes for the first time. He even gets the arbitrary gamma in there from Clausius. More remarkably, in the same paper, he derives the full Navier-Stokes system in the special case where the inverse power law is potential 1 over r to the 4th, force law 1 over r to the 5th. It turns out that's a magic case that you can actually compute inverses of integral operators for, and these are called Maxwell molecules as a result. Now, he thought he'd seen God almost. Because he comes from this and gets that the transport coefficients depend linearly on temperature exactly. And so he thought he deduced this 1 over r to the 4th intermolecular force law. However, a closer look at the experiments convinced him that wasn't quite right, but it was close. Next slide. So here's the Euler system he derived. You recognize the mass and momentum, and now an energy equation. This is the new thing. More importantly, he gets what the pressure is proportional to density times temperature. My theta isn't quite the temperature, it's just proportional to the temperature to make the equations pretty. And then you get this internal energy that's proportional to temperature as well. This pops out of his equations. You say, you look at that pressure law and you say, well, that should have been obvious. That's the ideal gas law. Well, the universal ideal gas law wasn't fully derived until after this. This is one of the theoretical foreshadowings of it. It really comes about, it was published in 1873 by Horstmann. All right. He also went further. He introduces what we might call an equipartition principle, which is a more refined case of what Clausius had used, and basically selected certain gammas for certain molecular models. Of course, the famous 5/3 for monatomic molecules we know today, but at the time he did this, there was no known gas that had this property. So, all right, somewhat academic gas at the time. For rigid linear molecules, 7 5 came out, and what was interesting about that is there were a lot of gases, the oxygen, nitrogen, so forth, that they knew fit this, but they weren't happy with the rigid molecular model. And then, of course, for nonlinear molecules, it would be 4/3. And if you only believed in rigid molecules, this is all you'd see. But of course, we see more than that. Anyway, it was a huge advance. It was the first time you went from a invertible microphysics to a macrophysics in some sense. Next slide. And then he gets the bottom line there just shows you the transport coefficients are linear. We don't have to dwell here. Let's go to the next one. What this work did was split physics into two major thrusts. The first developed statistical mechanics as we now know it, Clausius, Maxwell, Boltzmann, and Gibbs. But the second sort of rejected this view as unnecessary and unsupported, and these were called the energists, and it includes some non-trivial people like Kirchhoff, Rankine, Hugonio, and Doom. This matter gets settled in the early part of the 20th century after Einstein and Smoluchowski gave theories of Brownian motion that could be used in the experimental confirmation, and then Jean Perrin actually did this, for which he receives a Nobel Prize. Next. So just to wrap up quickly here, what Maxwell does is tie thermodynamics to fluids. And you notice that's been at the heart of your models that we've been discussing here in this symposium. It's really, you see the origin of the idea. Next slide. I'm not going to dwell on this. Next slide. This is just the Navier-Stokes and the closures. I'll go to the last slide. All right. So after 1908, it was understood that all fluids were compressible because we now understood that atoms and molecules were there, and that incompressible flow, as opposed to fluids, are derived from the governing compressible equations. And instead of one family of them, there's now a whole family of them, and that there's way too much time to, not enough time to talk about here. The universality is they arise in low Mach numbers, and when pressure fluctuations order Mach number squares. However, at the core of them is the motion equation of either Euler or Navier that we started the talk with. So I hope you learned something about the origins of some of this stuff. And I thank you very much, and congratulations, Elizabeth, on an impactful career.
I just about broke my brain, but anyway, Anyway, so any questions for Dave? Okay, well, hopefully, oh, yeah. We're perfectly on time. Yeah. Yeah.
I tried.
Yeah, yeah. No. Did you have some comments or thoughts?
Well, Dave was being very kind about my PhD, and I was going to give a little bit of background on that because I kind of expected him to, but he didn't do it. But I can do that later. We
Okay,
can do it now, whatever.
okay. It's up to you. It's your show.
Well, then let me have the microphone. I'm just gonna say a few things about my PhD, which really did not go well. Dave and Mac Hyman, who he also mentioned, saved my PhD. I wouldn't have gotten it without their help. And what had happened is I was in an applied math program at University of Arizona, and one of the professors there, Alan Newell, gave a talk about hurricanes. And it was just this fun little toy thing, but it's like, oh, I would love to work on hurricanes. This would be great. I was so excited about it. And so there was actually a professor in the atmospheric science department who was doing that. He worked on tropical cyclones. And so since I was an applied math graduate student, what they do in that program is farm them out to the other departments. And so I went to atmospheric sciences and worked with this guy. And he gave me a problem to work on, which, you know, sounded really good. It was fun. I got to study tornadoes for the first year. And so when I came here to NCAR the first time as a postdoc and saw the tornado machine, it was like, oh, that's so cool. I want to climb in there and play with it. But anyway, I started working on this problem. I'd been working with Mac for a while as a student at Los Alamos, working with him. And so he was helping me with the numerics to code up this tropical cyclone model. And so I did it. It took a long time because I was a graduate student. I didn't know what I was doing. But eventually I got the thing to run. I put in the forcing that my advisor suggested, and it collapsed. It just, no hurricane, nothing whatsoever. And it's like, what's wrong? I've got something wrong with my code. And so I brought it to Dave and said, Dave, I'm really having trouble with this, because he and Mac were co-advising on my committee. And Dave is amazing. He looked at it and said, oh, it's a homogeneous system. And if you're a math student and you've got a system of partial differential equations and they're homogeneous, the solution is 0. So the good thing about that was that my code was right. I was getting the right answer out of the code. The bad thing was that this idea that my PhD advisor had was never, ever going to work. It was just not going to work. And Dave actually helped me write a proof of that. And I took the proof to my advisor. And as you can imagine, that did not go over very well. So when Dave mentioned a redirection in my dissertation, we did. We moved it. We moved it back toward applied math. And so I did numerical analysis of the equations and just made it an applied math dissertation rather than an atmospheric sciences dissertation. And I will say something about that at the end, just what I learned from that experience. But honestly, I would not have gotten a PhD without his help and that of Mac Hyman. And we'll probably mention him some more later too.
Hey, thanks again, Dave. Hopefully Jerry's mic stuff has worked out. Did you guys talk to him? Jerry, are you there?
I'm here. Can you hear me?
Yay, we can hear you.
Okay, all right. I don't know what I
Okay.
did, but
So,
it's on.
do you
Okay.
want us to present your slides, or are you good with presenting them?
I'm good with presenting. Oh, yeah. Why don't you shift them, because I've got a squirrely mouse here.
Okay, sounds good.
Yeah.
It's
You have
coming
the
up.
file there, right?
Yeah, we
Oh.
have it. They're bringing it up now.
Okay, all right.
Just
And
let me know when you want me to change.
okay, all right. Can I make it larger or can you? Can we, yeah, there we go. That's much better. Okay, next slide. I have some pictures, the earliest ones I can find of Elizabeth. This is in their new home in South Santa Fe in 2005. The next slide, please. And this is Elizabeth, Steve, and my wife Isabel in Albuquerque in front of the Sandia Mountains behind here. Next slide, please. And this is more than 10 years later. We're at the Troutdale Airport, and Steve and Elizabeth are about to take off and fly from Portland, Oregon to Montana on a whirlwind trip through the West. Next slide, please. And it struck me as spectacular. These are rhododendrons, and they're enormous. Here's Elizabeth for scale, Steve, and my wife Isabel. Okay, next slide, please. Next slide, yeah. So when Elizabeth and I were talking about this talk, I told her a story about my interactions with Bob Malone, which I'll mention in a moment. And she came back with this remark: there are so many points in time where my career and my whole life might have gone an entirely different direction. Usually I think of those as my own doing, but everything hinges on something or someone who came before. Next slide. By the way, Apple Intelligence reacted to that comment by saying perceptive remark, which is a little disquieting. Elizabeth just told about this, and I learned something from that. I didn't know some of the details, but Dave Livermore bailed her out on the thesis by telling her, "Oh yeah, that really is unsolvable," and gave her another direction to go. Mac Hyman and Dave were both students of Peter Lax, and they arranged for Elizabeth to work at the Center for Nonlinear Studies at Los Alamos. And my first interaction indirectly with her was with Bob Malone. He was in my group in magnetic fusion at Los Alamos, and he was working with another scientist on a one-dimensional model of a fusion device, fusion experiment. And I was at that time working on a three-dimensional model of an experiment and learning all sorts of new things. And I wanted to perhaps recruit Bob to work on my project too. And I was unsuccessful at persuading him to consider modeling in more than one dimension. By that, Bob avoided becoming famous for discovering convective mixing of stars, which he had worked on at Cornell University under Salpeter. And he instead created the climate modeling program at Los Alamos. And I told Elizabeth if I'd been just a little more persuasive, none of that would have happened, and she wouldn't have had the career that she had. That was the motivation for the remark before. Next slide, please. Next slide, please. Yeah. Dan Butler was a leader of the theoretical hydrodynamics group, T3, that Elizabeth spent her entire career in. And I think it was around 1994. He asked me, would I mentor her? And I don't know the circumstances behind that request, but Elizabeth came to my office and we talked for maybe 5 minutes. She said, well, she already had something to do. And it turns out that that was something to do with John Dukowitz. And John and Elizabeth had recognized the potential for the elastic viscoplastic material model to model sea ice. And so that was really the start of her career in this field, in the field you're talking about. Next slide, please. This is John, and the picture was taken in 2004. But last time I saw him, he looked pretty much like that. The guy still has all his hair, and he looks very fit, and he's doing just fine. Next slide, please. Okay, Elizabeth faced some difficulties at Los Alamos, not insurmountable, as obviously her career shows, but when she first worked at Los Alamos in T3, she was working in a group that Frank Harlow had founded many years before, and he was famous as a pioneer in computational fluid dynamics. And in the 1960s, he wrote several papers with Martha Evans, a woman that I was told was called the Bat Lady because she always wore a cape. But Martha hid Frank's badge in the women's room at the end of the workday and left. And Frank was very much a man of his time, and he although he couldn't get past the guards, he also would never ever go into the women's room. And I don't know what the resolution was. I said, well, who got the badge for him? And I think a janitor did, but I'm not sure. And from the kind of friction that would generate that kind of response from a woman, it had degenerated to what I call an anecdote versus a legend. In the 1960s, or 1990s rather, Hans Frauenfelder was director of CNLS, and he was, I think he was Swiss. He spoke with an accent. He was a very imposing personality, and he told Elizabeth to perform secretarial work to help organize a meeting. She didn't hide his badge, so it wasn't that much friction, I suppose. She just didn't do it, and she got away with it. Next slide, please. My professional contacts with her were minimal. I was in a completely different field, but I was editing the Journal of Computational Physics at the time. Elizabeth wrote a paper. She asked John Dukowitz, who was an associate editor on the same journal, if he thought it was suitable for the Journal of Computational Physics. And Elizabeth told me he told her that it needs work. Shortly after that, she showed it to me. I read it and suggested she submit it. It reviewed well, and I thought it's nice to have something from a new field in the journal, so I chose a figure from her paper for the cover. And the paper was published, and it's been cited many times since then. Next slide, please. Elizabeth reminded me to mention lunch. This was something that I started doing when I had a large number of Italian students at one time, Italian graduate students, postdocs. And the first one was Giovanni Lapenta, who unfortunately died last year. But he had brought in others who worked with him, and I would get together with them for lunch every day to try to keep track of what they were doing and to be available if needed. And I was behind the fence, and so was Elizabeth, but I invited her to come along to the lunch meetings, and we had a good time. And she thoroughly enjoyed that. She told me that that was one of the highlights of the early years that she was at Los Alamos. It wasn't great food, but it was great company. And I put that forward as I didn't realize it had so much impact on her, but I put that forward as an idea that other people should copy, and that to note that great institutes like Courant, Max Planck, and École Polytechnique in Palaiseau, France, do something similar. At Courant, it was coffee at 4 p.m. on the 13th floor. Dave probably remembers that. And then at Max Planck, we would gather at this long table after lunch and have coffee together, and everything was discussed then. And the École, there was no formal gathering, but the food was great in the cafeteria and everybody went to lunch. Next slide, please. So if I was looking in Elizabeth's papers for the figures that she had shown me previously, showing how much of the Arctic was clear of ice in successive years and in different seasons of the year. And I couldn't find anything that I could copy in here. I just didn't have access to all of them, I suppose. But I want to make a comment about the present regime in Washington. You know, we're looking forward to a future without ice in the Arctic. And if you look at the depth of the Arctic Ocean, it's deep. These are, you know, almost all of this is navigable, and soon it will be clear of ice. So it's going to be a future with deep water ports for Russia and an accessible Greenland. And that may be the motivation for saying that Trump is going to make Canada the 51st state and to take over Greenland, whether Denmark wants it or not. And it strikes me as kind of peculiar because our friends in Washington have recognized consequences, even as they deny the cause for the changes we're seeing in the world we live in. And I had no idea. It's with new appreciation of Elizabeth's role in climate modeling and how much she's contributed to the ice. And I'm glad to have heard about it today. Thank you. Yeah.
It's just great. Yeah. Thank you. Any comments or questions for Jerry? Okay, well, yeah, thank you so much. We're going to break for lunch now. Okay, well, it's 1:30 and people are shuffling in, so continuing with some of Elizabeth's mentors, we have the one and only Steve Ackley online. Okay, you're ready to go.
Okay, well, thanks, Dave. And hi, everyone. Some people haven't seen for a long time, Danny and others. And I'm very happy to be here to talk about some work that started with Elizabeth. And you can tell from the shameless paraphrasing of Marika's title that the subtitle of this is 2 months of adventure on the actual ice with Elizabeth Honka. So next slide, please. So this work was on the Ronnie Polinia in front of the Ronnie ice shelf. And I don't know if it's in the Weddell Sea side here, that blue area that's shown on the in there. And what happened was that this is a large opening of the Ronnie Polinia, as you can see by this time sequence of SSMI imagery from December of 1997 through February of 1998. Next slide, please. So the adventure with Elizabeth was on the HMS Endurance cruise, which he made in January, February of 1998. And this slide shows the cruise track that we were there. And you might remember the opening slide showed Elizabeth holding an ice core And that was probably on the left-hand side of this here, shown by the diamonds in the figure where we took ice cores. And in the background is the black coast of the Antarctic Peninsula. And this was probably the first time that any ship has gotten into the Black Coast, which signifies the unique opening of the Rani Polynya at this particular time. The next slide. So the major cause that we've attributed to the opening of the Rani Polynya was a change in the winds in November of 1997 that continued throughout December and January of 1998. And what you can see in the top slide is the November climatology, which shows sort of weak easterlies coming into the area of the Rani Polynya, as opposed to the actual November 1997 winds, which were quite strong southerlies coming off the Antarctic continent at that time. And that was unusual compared, at least, to the climatology. The next slide. So Elizabeth conducted the SEIS simulations. This is, our early SEIS, I'm sure. There's been many iterations since then, so I'm sure that there's probably been some updates. And the three simulations were the control simulation with the climatology, the era, ECMLW winds climatology, and then it was run with winds, and then finally with no shortwave radiation in the top to bottom sequences that we see here. And you can see in the control sequence that there isn't a major opening of the Rani Polynya, whereas in the winds we can start to see the rather large opening that's taken place. I want to draw your attention also to two black spots in this area here. I'm showing it on my, you probably can't see my pointer, but just to the east of the white spot are two black spots with rather large icebergs that were grounded in the Weddell Sea for a long time, and they happened to break loose in that particular year, and were floating a little bit northward. And I'll refer to those later as perhaps another factor in the opening of the Polynya. Finally, when no shortwave radiation was run, we also, but with the same winds, we see that there's not a major opening of the Rani Polynya at that particular time, indicating that there was an effect of the radiation that was coming into it at that time. So next slide, please. So in the closing of the freeze up of the Polynya, we can see that on the left-hand side, the SSMI imagery shows a sort of central area that was open into March. And on the SEIS simulation, you can see that that's an indication of the thermodynamic freeze up in there. It was controlling the freeze back of the Polynya starting in February, March. Next slide. So this slide shows the ice fraction and the heat fluxes at 7550 north, and it shows the effect of the incoming shortwave radiation. And if you take a look at the right-hand side, the November shortwave radiation is starting to overcome that, and because there's open water there at this time, because the winds that are blowing off rather than ice formation, there's a heavy absorption of shortwave radiation and downward long wave, and now that causes the ice not to freeze immediately, even though there might be enough sensible and latent heat for it to freeze because of the open water albedo feedback. And you can see that there's a rather marked difference between the open water areas on the right-hand side in terms of the incoming shortwave, which serves to keep the Polynya open for that prolonged period. So it's basically driven by the winds, but then controlled by the incoming shortwave radiation. I might add that this November opening of the Rani Polynya, even though it's a one-time event, is really emulated by the opening of the Ross Sea Polynya, where you can time to practically the same day in November when the ice stops freezing in front of the Ross ice shelf, and the whole Ross Sea, in that case, starts to open at that time in early November. Next slide, please. Now, getting back to the effect of these blocking icebergs, which might happen, this slide shows the cruise of the Endurance of Shekels and Endurance, and it shows the effect. You can take a look on the bottom side. The Endurance was beset in January of 1915, and then drifted basically northeastward for quite a while. So this serves to bring ice in from that eastward side. But because the icebergs were there in 1998, they could have served to help block that incoming ice, and perhaps led to the increased opening of the Rani Kalinia that was observed in SSMI, but was not as wide as seen in the SLICE simulation, which was basically driven by the winds. Next slide, please. Oh, in contrast, I'll talk about the winter Kalinia, and this is from some work we did in a cruise in 2017 into the Terra Nova Bay Kalinia, which is on the left-hand side of this cruise track in the Ross Sea. Next slide. And this slide shows the deployment of several of these Swift buoys, which are wave measuring buoys that Matty Smith deployed during this particular cruise in the area of the Terra Nova Bay Kalinia. On the south side of Terra Nova Bay is this large ice tongue, is the Drygalski ice tongue, that essentially blocks the incoming flow of sea ice from south of there, and allows the katabatic winds to drive the ice away from that without incoming ice coming from the south. And so I think this might be somewhat of an analog to what I was mentioning about the Rani Kalinia and that affected the icebergs blocking it. So on the right-hand side, we see that these Swift buoys are measuring the significant wave height in the top panel, and you can see that, or the wind speed, excuse me, in the top panel. And so we're seeing 20 to 30 meters per second in the instance on the green things on the 5th of May. And this led to significant wave heights of up to over 2 meters in that particular area. So that's the major effect that I want to address here, is that we're seeing rather large waves in the open water areas of the Terra Nova Bay Kalinia when we have these katabatic winds of 20 to 30 meters per second coming out. The next slide shows. This is a deployment from the Swift buoy, showing the wind speed, the wave height, and below this is the RMS slope of the waves within that. And I draw your attention to the left-hand side of the bottom slide, which shows the increased amount of RMS slope and the early deployment of the Swift buoy. The buoy was deployed in one of these open water bands as shown there, but after a couple of hours, it became incorporated into one of the ice bands there. The effect of that, shown in the next slide, is that the wave energy spectra was, in the early part, was dominated by these, had a large component of these very low, high frequency waves with increased surface slope. And then as it became incorporated into the ice cover, as it was infected northward, then the high frequency portion of the spectra was damped out, so there weren't any more high frequency waves. Next slide shows. So the effect of the high frequency waves is to, with the increased surface slope, is to cause them to break. So you have breaking waves, and you can see in the open water area, and it's not quite clear in here, but you don't really see any breaking waves in that ice-covered area. But it was surely shown on the spectra that we saw before. Next slide, please. So the effect of these breaking waves is to generate a large amount of sea spray. and sea spray advects into the atmosphere. And Peter Guest, who was the meteorologist on board, was able to see what that effect was on the heat balance of that. And this is based on a dear friend of ours, now deceased, Ed Andress, who had worked on both Antarctic problems, but also the effect of sea spray on heat balance in tropical cyclones. So the next slide shows the effect of sea spray icing on ships is quite dramatic. You can see this heavy ice build up on the deck of a ship as it is impacted by these breaking waves. Next slide. So the effect of the sea spray is shown in these calculations that Peter did and measurements. On the left-hand side, you can see these diamonds, and this was a direct measure of the heat fluxes in front of the ice shelf, the Nansen ice shelf in Terranova Bay. And what this was done was to use parameters of wind speed and temperature in the near coastal region, and then radiosonde balloons that were there so you could close the heat balance in between these. And what we're seeing on the left-hand side is the effect of the very large amounts of measured heat fluxes, total and sensible, and interfacial is with just the wind speed over the sea ice surface. And the effect on the sensible heat flux is essentially to double the interfacial heat fluxes, so we get upwards of 2,000 watts per square meter in the open water areas very near the ice shelf, out to about 30 kilometers north of that. And this is because you're getting about an equal contribution to the sensible heat fluxes from both the spray and the interfacial components. The latent heat fluxes are less affected by spray, and so predominantly the latent heat fluxes are from the interfacial side. Next slide. So combining these into the heat fluxes, we can see that the sensible rate and the total heat flux is almost dominated by the sensible heat flux of the smaller component from this, and a very, very small component from outward long wave radiation. We're in polar night at this particular time, so no incoming shortwave at all. So the next slide. Well, this is a calculation that we did based on those heat fluxes and related it to the ice production. So using the wind speed at the coastal station Manuela over the month of May of 2017, and we had occupied this area till about the 10th of May and made those measurements that I showed in the earlier slides. And first two slides show the wind speed and air temperature and relative humidity from that station. And the next slide, the third from the top, excuse me, I didn't mean the next slide. Yeah, thank you. We see that the third from the top shows the no spray sensible latent heat flux, and on the left-hand side, those are watts per square meter. On the right-hand side, we're seeing what that amounts to in terms of ice production. And the scale is a little small here, but we're seeing basically 20 centimeters of ice production, basically from a total of maybe 30 centimeters on the right-hand side of that, up to 40 centimeters, based just on the interfacial fluxes. And this is per unit area in the open water areas of the near coastal region. When we add on the fourth from the top, second from the bottom, we see that the no spray and spray heat productions are shown, and we can see that the spray and heat production, the blue slides, is dominates many of the areas and leads to a much higher ice production in centimeters per day, up to about 60 or 70 in the highest portions. And this leads to the bottom slide, which shows the ice thickness in centimeters per day. And we're seeing that the difference between the spray and the no spray is, like I said, is almost a doubling on certain days. So next slide, please. So the conclusions, the Rani Polania, that we see the winds and end of the freezing and radiation fluxes in summer caused the Polina opening, historic opening in 1998 may have been enhanced by iceberg blocking of the inflow of ice from the east, possibly, although we probably should check the winds over a long period of time, but at least up until 1997, as the climatology shows, we hadn't seen neither an opening of the Rani Polina nor perhaps these anomalous winds. The Terra Nova blade and the radiation fluxes are really dominant in terms of this, in terms of allowing the Polina to stay open. In Terra Nova Bay, Polina, we have cataback winds and freezing, only the sensible latent heat fluxes, no radiation fluxes, and strong advection of the newly formed ice gives very high production rates because you're seeing a constant overturning the ice factory of the Polina as ice is pushed out by the high winds as well. The high winds cause breaking waves with sea spray in the open water areas near the ice shelf front and lead to a doubling of heat fluxes and much higher ice production. And this is, you just integrate that bottom area that is seen. We're seeing basically 14 meters per month in May versus 9 meters from just the sensible heat, just from the interfacial fluxes. So I'd just like to conclude by saying that it was a great experience with Elizabeth on there, and you can tell by the big smile on her face that she really enjoyed that time there, as I did, and I wish her well in her retirement and hope she'll come over and see Jackie and myself in San Antonio sometime. Thank you.
Thanks, Steve. Any comments or questions for Steve? Okay, so we're going to move on to a series of talks sort of from the CESM perspective. And to start us off is Cecilia Bitts.
I found it. Oh, thank you. Okay, great. Well, I have a talk today prepared to tell you a little bit about history of my interwoven work and friendship with Elizabeth, and also some science. So this photograph is from 2002 when Elizabeth and I shared the CESM award that year. Actually, it was the CSM award in those years. And so I think I first met Elizabeth in 1998 when I attended the annual meeting. And in those years, she had already given her EVP model with the Sempner thermodynamics to the PCM, and it was in operation. And we were just kind of assembling the first CSM model at that time. But it didn't have a sea ice component. Anyway, I basically messed up the thermodynamics in the PCM by, or I should say mucked with it. I think it actually was a success, but by adding what is now called the Bitts and Lipscomb thermodynamics scheme, as well as the ice thickness distribution. And I'd say the basic architecture of the model is still the same, with it enabling an ice thickness distribution and this excellent EVP thermodynamics code, plus a lot of other options that build on those two things. Even though I am going to talk about thermodynamics, I guess I should acknowledge that Elizabeth, of course, is really famous for dynamics. And I looked up, she has 1,600 citations on her EVP paper, which is really an incredible achievement. But if it weren't for that EVP model, which was such an innovation at the time to permit really the leading edge dynamics that we could afford in climate models, none of this would have been possible. And then her contributions to actually adding all this additional thermodynamics is really extraordinary. So she may be famous for dynamics, but she's definitely well known for her thermodynamics too. And these are just some of the things she did. In fact, I kind of got tired listing them. But I started to read a lot of your papers in the last month, which was just a total joy. And I hope I can tell a little bit of a story about them today. So what I'm mostly going to talk about is the mushy layer thermodynamics and what we can do with this terrific resource. So sea ice is a two-component, salt and fresh water, two-phase, ice and water, and it's called a porous reactive media because where the salt is, and as well as the temperature of the ice, influence its structure. And then in turn, the structure influences the availability of salt to move around and heat to be conducted and actually conducted in the ice as well. So if we look at a little bit of basic math, this mushy layer involves modeling a fraction of brine that's in the pores, that's known as porosity, and then 1 minus that fraction is the fraction of ice, but through a really clever way of doing so. So there are other examples of mushy layers, but sea ice is kind of unique because the whole of the slab of ice is a mushy layer, where the other kind of famous example, metal alloys, it's at the solid liquid boundary only, but here it's all of it. So we have a really big mushy layer. We're lucky. Yeah, and phi is this component that actually is varying in space and time. And one way to actually talk about it is through how the temperature influences the pores. And these are a series of 3 photographs that Bonnie Light took that I think you have to maybe squint a little bit, but if you look carefully, you can see that as the ice is warmed in the lower panel compared to the upper panel, the brine pockets are bigger. And that's because the brine is obligated to stay at the freezing point. And the way it does that is by diluting itself. And so when it warms up, the brine has to melt some ice so that it stays at the salinity that essentially allows the temperature in the brine to be at its freezing point. This is a linearization of that equation. You can add some more terms if you like. The first, though, I think realization that some cool action was happening in sea ice was given by Worcester, and he argued that it's a porous medium that actually undergoes convection. So there's actually a upwelling of brine in the sea ice in what's known as the mush, and then there are these wider channels where it's going down back to the ocean. And he described this with a porous medium Rayleigh number. So though what's kind of cool about this is due to this convection that's occurring in sea ice, it's drawing up what surprisingly is relatively low salinity seawater and replacing what is the relatively high salinity brine in the sea ice. So it's desalinating through this process under normal circumstances, but of course there are other ways it can desalinate as well, which we simulate in the mushy layer, such as when snow at the surface produces fresh water, and that is pushed through the brine channels. But a very important part of the science that this convection enables is what Nicole was discussing earlier, which is incorporating algae and other biological material in the sea ice, which I love these creatures. I think they're aliens, but whatever. Anyway, a real photograph, which was actually also shown by Nicole. I think we need some more photographs, since the 2 of the photographs I have are both ones that she showed. But you know, the algae in sea ice is super important for Earth's atmospheric composition and the whole biogeochemical cycles in our world. But the picture that we came up with, and I say we very tentatively because I had almost very little to do with it, but I'm co-authoring on this paper very generously from Adrienne Turner and Elizabeth, with the picture that we tried to model this mush in that was the dominant area, and then the narrower channels and the flow of the seawater upwards in the mush, as I described earlier, is actually simulated. And We do it in a one-dimensional way, though, two different types of material, so the mush and the channel. But it's really pretty sophisticated for an Earth system model. And I think that we ought to, we need to recognize that, because, before Elizabeth got involved, Earth system models sea ice was so simple. It didn't give us the opportunity to do cool science in the one dimension and then test it and explore what it meant for climate. And now we can do that, which is such an amazing thing. So this mushy layer model simulates the salinity, and this is old data from 1927. Oh, I actually love this figure. It's in that one of the Turner papers. We don't get exactly this in all instances. It's showing the seasonal cycle of salinity, but we get these general structures of C shapes and S shapes, and freshening during summer, and higher salinity during the early growth phase. And of course, we can't forget the math. It involves two beautiful equations that are solved to solve for the mushy layer dynamics. And the first one is essentially a heat equation that Q is a enthalpy of the sea ice, and it's related to the temperature as well as the salinity. But it's essentially like you could recast that as a temperature equation, and then a salinity equation. So you have a choice of which state variables you want, Q and S or T and S. But we usually have written it in terms of Q and S. And then the last point to make is that this enthalpy represents the fact that some of the ice is already melted in the brine, and some considerable fraction is melted. So that's why it's porous, and it is soft if you squish it, right? And it's cloudy because of those pores scattering light. But that essentially is reducing the amount of energy that then takes to move the boundaries at the top and the bottom. So we could have a larger seasonal cycle of sea ice thickness change because of this physics, essentially. But it's also changing the surface temperature because these brine pockets take up energy and sort of store it and shift the temperature phase at the surface, phase in time. Anyway, so now to get to a little bit of consequences. Well, the sea ice mushy layer is more porous at the beginning of the melt season when the salinity is high and the temperature has warmed up. But as the season goes on, all the flushing from snow can actually lower the salinity at the surface, and it can actually become less porous for a time, or even so porous that it drains all the sea ice and then becomes less porous, which I think is what we're seeing here. So these pictures from quite some time ago, the North Pole webcam showed this really complex pond coverage changing over the course of the seasonal cycle, and that's directly related to the mushy layer physics in the sea ice. And now we can actually explore this science. And so another kind of cool paper by Polishevsky kind of tried to describe the evolution of the brine channel size and salinity in this paper. And we can test this now because we have all this physics in our model. So I'm going to show a little idea that I got involved with because this paper came out, I think it was 2016, that said we could thicken the sea ice by adding seawater to the surface. And I thought, wow, that's crazy. And I'm going to show why I think it's crazy. So I sat down and thought about it, and I was like, well, okay, if you thicken the ice artificially, it'll be thicker so that it'll grow less thick in naturally. But let's look at that physics for a moment. But first I wanted to say that what this might be good for. And it might be, I think, the goal of some to thicken the ice and cool the climate. But I think another really worthy goal of maybe doing this would be to help villages by thickening the ice right next to locations that have a threat of wave degradation and erosion. So I don't think of it necessarily as a geoengineering option, but maybe also as a mitigation option for villages if this was a success. So it's worth thinking about. Anyway, natural sea ice grows at the bottom of the Arctic sea ice, and it conducts heat from the ocean. And so you can calculate the rate of the growth is inversely proportional to the thickness, because it will grow faster when it's a poorer insulator by conducting more heat. And that's roughly, an estimate assuming linear temperature profiles. So I thought, okay, if we thicken the ice, it'll be thicker, so it'll grow more slowly, naturally. So we're not going to get anywhere by making it attempt to be thicker in a climate that isn't inherently designed for that thickness. So I said, okay, but I got to test this to make sure I'm right. So I took ice pack and added some water at the surface with a mushy layer physics, and so it was salty water. And I made a slush, and that immediately will freeze in the model, which you could debate is wrong or right, but in winter it should probably take very little time to refreeze. And so what happens is you have less snow and more ice. And if you're thinking about this now, the right way is to realize, wait, snow is a really good insulator. So what we did was actually replace some of the snow with some ice, which is a much poorer insulator, and the whole layer is a poorer, better at conducting heat, so poorer insulator, and it naturally grows at the bottom much more fast. So I was totally wrong, and thank goodness for ice pack, I could find out why I was wrong. And we did some full simulations, first in ice pack. I think I'm running out of time, so I'll just say we tested like the seasonality and how much and when should we add it and when shouldn't we add it, because you obviously don't want to wash the snow away in spring. And what we found was you could do pretty well, say by adding 30 centimeters of seawater, you could grow almost a meter of ice under the right conditions. And so we plugged this into the full Earth system model. It's very sensitive to when you start, so I won't go into the details, but basically this just enabled us to really test a potential hypothesis that could help people. And of course we didn't limit it to the villages, we actually put it everywhere. But I think the next step would be to go back and see where it could be the most beneficial, and considering the cost as well at the same time. Anyway, so I will just end there and say thank you that you've created this awesome resource that can test hypotheses because it has so much physics in it. Yes, it always has the potential to have too much, but you don't have to look at everything. And as long as it's thoughtfully developed, I feel confident using it despite all of the complexity when I know what the thing I want to do is working well. So I'll just end with thank you to Elizabeth. And please come visit now that you're on.
Any comments or questions for Cece? Okay, all right. Well, now the other half of the Bits and Lipscomb Thermo. Yeah, he needs the mic. How about here on your shirt? So, yeah, that should be fine. The next button. Yep.
Light.
I'm not. You can press and hold it and see if the pointer comes up. I don't. Anyway.
All right. Okay, God, it's great to see so many people here I've known for a really long time. And Elizabeth, it's just so great to be here to celebrate your retirement. And this will be, to some extent, review from what Dave Bader talked about earlier. But I want to talk about the early history of SEIS, and the early history goes back to the early history of the COSM project at LANL. And I too have a copy of Bob Malone's professional memoir, which is called Ocean and Sea Ice Modeling in the High Mountain Desert of New Mexico, a personal's perspective on how COSM came to be. If anybody's interested, it's a wonderful, interesting memoir. And so Bob came to LANL in the 70s and sort of accidentally became the first climate modeler at LANL, although he actually hadn't studied climate modeling before. So he decided he needed to learn about climate modeling, and he would come to NCAR for a couple months in the summer and hang out with Warren Washington and people like that. And then in 1983, nuclear winter became a big hypothesis, a big thing. And Bob started a group at LANL that worked on nuclear winter and had some amazing success in a fairly short time. And then that funding went away for a few years. But then in 1991, the DOE CHAMP program, led by Dave, began. And Bob had some support again to do climate modeling. And he made the very wise decision not to focus on the atmosphere, but to focus on the ocean and later on the sea ice, because he recognized that was a problem that you could attack with a relatively small group of clever people. And was very, you could make a lot of progress with parallel computers and new computing techniques. So Bob hired John Dukowitz and Rick Smith, neither of whom were climate modelers before that, to develop POP. It was a huge success. And then, quoting from Bob's memoir, we badly needed a sea ice model to complement POP, so Elizabeth and John Dukowitz repeated the POP experience by completely rethinking traditional approaches to sea ice modeling. So Elizabeth came to LANL as a postdoc in 1994, and soon set out working with John to develop the EVP model. My first contact with Elizabeth, the first time Elizabeth and I met, was my very first climate modeling workshop, which was at the University of Victoria in the summer of 1996. And this was such a great workshop. By the way, I never throw anything away. So I still have the third circular from the workshop. Yeah. So yeah, if anybody wants to see some history, right here, I'll show it to you later if you want. Anyway, really fun workshop. And the participant list for the workshop is actually astounding. It seemed like everybody came to this workshop, and not just people who were relatively famous and senior, but people who were not at all famous and very junior. So this is just a couple of pages that I picked out from the participant list, and you'll see some legends of ice sheet and sea ice modeling. For example, Bob Benshadler, who later became a good friend, Antarctic glaciologist. Bill Budd, who was receiving an award at the meeting, also a legendary Antarctic ice sheet person. And Bill Hibbler, who by then was already very well known for developing the viscous plastic model of sea ice. But if you look more carefully at this same list, you'll see some younger folks. For example, Dave Bailey. Top right, Marika Holland. And just below, Elizabeth Hunke. Now, Dave and I don't think we met at this workshop, but I met Marika and we had a really nice dinner, I think the last night of the workshop, and I met Elizabeth. And I don't remember if you gave a talk there, but I remember that we walked down to the waterfront during one of the breaks and we talked about sea ice modeling. And one of the things that was striking to me at this workshop was that you had these fairly advanced sea ice modeling ideas. Bill Hibbler on the dynamics, my advisor, Norbert Untersteiner for thermodynamics. Alan Thorndike, who was on my committee, had sort of pioneered a model of the ice thickness distribution. But for some reason, the global models hadn't taken up these advances yet. And I thought that was a really ripe area for research. And Elizabeth thought so too. And so at that time, I don't think it was quite finished yet, but she had made a lot of progress in the EVP model and talked to me about it. And I'm sure I asked you, how is it that you do sea ice modeling and ocean modeling in the high desert of New Mexico? And not for the first or last time, you explained it very patiently. It kind of goes back to nuclear winter and all that. But anyway, I thought the ideas that you shared with me were really, really fascinating. And so I was interested the next year when the initial EVP paper by Elizabeth and John came out. And again, Bob's quote, the EVP rheology addressed the most pressing shortcomings of sea ice models. And then Bob says, at first, the entrenched traditionalists, and Bob's a very diplomatic person. He He doesn't name names. You can speculate if you like. Refused to accept this new approach, but repeated comparisons show that EVP was better both physically and computationally. And so within a very short time, the model was well known and embraced by the community. So meanwhile, back in Seattle, I'm finishing my PhD. 1998 was a really eventful year for me. Among other things, finished my PhD. I went to Sheba on the Sheba project to the Arctic and spent a couple of wonderful months in the Arctic in the spring. And that's me next to a very tall sea ice ridge. And then after I got back from Sheba, I went for the first time to this, what was then the CSM workshop in Breckenridge. This was the first of 25 such workshops I've been to so far, and still hope to get to many more. I almost didn't get to the workshop because, well, in those days, I didn't have a laptop. So the talks we gave were with transparencies. So this is the transparency from the first talk I ever gave at a CSM workshop. Anyway, as I always do, I stayed up late working in my talk the night before. So went to bed late, packed my suitcase, set my alarm for about like 5:45 because I was being met at 6:30 by people from the UW who were going to go to the airport. So give me a ride to the airport. So I figured I'd have time to shower, eat breakfast, and then go catch my ride. So I don't know what happened, but my alarm didn't go off, and at 6:25, I woke up. And at 6:30, I was there to meet my ride. Thankfully, having packed my suitcase, I wasn't fed, I wasn't washed, but I was there. And if I hadn't made my plane, I'm not sure what would have happened with my career, but thankfully I did. And while I was at that workshop, I presented some of the research I've been doing for my thesis. And I met Bob Malone, who I didn't know about before. And Bob explained, told me about COSM and the great work they were doing. And he told me about Elizabeth, who I already knew about. And he said that he thought what I was doing would nicely complement what Elizabeth was doing. So why don't I come down for an interview and check it out? So I went down to New Mexico for an interview a month or two later. Let me say a little more about this. So I go down I fly to Albuquerque, I rent a car, and I drive up from Albuquerque through Santa Fe to Los Alamos. A lot of you, I'm sure, have done that drive or commute many, many, many times. So I'm thinking about, do I want to live in New Mexico? And somewhere between Santa Fe and Los Alamos, I make the decision, I should have been born here. I love this place. If they offer me a job, I'm going to accept. I'm going to move to New Mexico. I'm going to settle down. I'm going to raise a family and stay here as long as I live, which is almost what happened. The only thing is that I'm temporarily living just north of the border. But Jerry and I do plan to return. At any rate, love New Mexico, love the group at LANL, felt really welcome there and was offered the job and joined later that year. So, and then it was a really exciting time to be in COSM. You had Bob, who was the nicest person you ever met and just a great first boss. And Bob died about 5 years ago with complications from Parkinson's, and he's someone I really miss. Anyway, so this group, Elizabeth and John, were my postdoc advisors, and they were such great advisors. I arrived in Los Alamos basically with $10 and a floppy disk in my pocket. And the floppy disk had a copy of an F-77 program for sea ice thermodynamics. And that was like all I knew about coding. And I don't have the floppy disk. I'm sure if I dig around in my garage. Anyway, Elizabeth was very patient and sort of showed me the ropes, showed me how to work with a big model. And over time, we were able to put in the thermodynamics that Cecilia mentioned, and we put in an ice thickness distribution in the model for the first time. And by the time I finished my postdoc, about 3 years later, we'd released version 3.0, which had a lot of really good stuff in it. And I do have this. This is the Decade of Progress report from 2001. the stuff in this report is just remarkable. What Bob and his and this team were able to accomplish in 10 years still blows me away. And one of the things that blows me away as much as anything is 2001. EVP has only come out 4 years ago, and this is the list of user communities for the SEIS model. Elizabeth built an international community. There's like 9 different countries here in such a short time and was helping all these people use the model. I have no idea how you did that. But anyway, some of the users here, including some folks in the room that we'll hear from later. So after my postdoc, thankfully I was stayed on as a staff scientist, and we did some, kept developing the model. And by then I was sort of getting the hang of how to work with a bigger code, and we put in the remapping transport and improved the ridging, and we did some software stuff like rewrote everything as F90. And by 2004, we were able to release CEIS 3.1. And in the meantime, we're working really closely with the folks here at NCAR. Cece mentioned the Distinguished Achievement Award, which she and Elizabeth shared, for bringing state-of-the-art CEIS modeling into what was then CSM, which had never been done in any Earth system, climate system model before. So it was a really, really big deal. And by 2004, we were ready to release version 3.1. And interesting, that's February 25th is the release date. And that's within a few days when I went to Antarctica for the first time. So I was tired, I needed a vacation, so I went south to McMurdo Station and got on that ship, the Nathaniel B. Palmer, and then had about 6 weeks sailing around the Ross Sea. I think Steve Ackley actually helped me make that connection to be on that cruise. So I was doing sea ice observations for some time. That was really fun. A little bit of biology observations as well. And when I came back, very refreshed and ready to go again, I knew we had made it big because at Los Alamos, which is not best known for its contributions to climate modeling, there was a writer for the newsletter who wanted to interview Elizabeth and me to be on the cover of the LANL newsletter. And the writer thought it was really interesting. We were doing sea ice in the high desert. So they wanted to do the photo shoot in the high desert. And so there we were with a friend I brought back from Antarctica. And then Bob in his memoir wrote at this time, now EVP has been adopted by almost every major modeling center in the world. So the history of SEIS goes on and on, but for me, that's a nice stopping point. That was the period when Bob was still leading COSM, and it was just such a fun time. Things were developing. Didn't necessarily seem that way at the time, but in retrospect, things developing so rapidly. And then the rest of the history you'll hear more about later. But I thought I needed to say something about pronunciation and acronyms. So pronunciation. When Elizabeth invented the model, she pronounced it sea ice because it was a sea ice model. And anyway, I thought that was really cool, but it was confusing as all get out to some people. So in the UK, for instance, they decided they couldn't call it sea ice. They called it SEIS instead. But people in other countries picked up the model and called it different things. So in French, cis. Italian, this is actually my personal favorite, chiche.
Yeah.
And Japanese, shiaisu, more or less. But some years later, I think around the time the consortium was formed, it was decided that there needed to be a standard pronunciation agreed upon, and the British pronunciation run out, and now it's SEIS. And there's a Wikipedia article, and the Wikipedia article says I think that's the same thing, SEIS. So that's been settled, but it was fun for a while. And then it started off also not being an acronym. And then for a short time, there was a sort of a move to call it the Community ICE Code, which is a bit of a strained acronym, but that never really caught on. So now it's just SEIS. It is what it is. So sometimes younger scientists will ask me how to be successful in climate modeling, and I'll point to Elizabeth as an example of someone who's extremely illustrious and successful climate modeler who's given so much to the community. And it's very simple, not easy, but simple. First, you make the best model in the world, and then you give it away. And that's what Bob's vision was, and that's what I think your vision was from the very start. And now most climate modelers who I know are pretty nice people, but being nice is not the only reason we give the model away. Because I think we've all experienced that when you have a community out there who you're serving, it raises your game. You have to be more careful, more clear, more creative. You find out what people want and need, and that feeds back into the model. So the more we give it away, the more we get back. That applies technically. It also applies personally with friendships. So I just feel so lucky that from the pretty early days, I got to be part of the development of this community model, which is, of course, still the best sea ice model in the world. Elizabeth has also been a good friend for many years. Photo Elizabeth and Steve was taken 2006, the day that my wife Jerry and I were married in Corrales, New Mexico. And Elizabeth, for her, we got a lot of the traditional wedding gifts, you know, China and such. But Elizabeth's wedding gift was do you still belong to this group, or is that your a quintet of amazing woodwind and players, and Elizabeth is the horn player. And they did the music for our wedding. They did Handel's Water Music as the intro, and they did Beethoven's Ode to Joy as the walking out. And then in the middle, our hymn was the Shaker hymn, Simple Gifts. And on the right is the music for Simple Gifts, arranged by Elizabeth Hunke. So she got her quintet together and wrote an arrangement, which they played at our wedding. And I thought Simple Gifts is kind of a nice metaphor for, for how Elizabeth is related to people, including me. When I first came to LANL, it was the gift of teaching and patience and waiting for me to sort of come along until I could be a full contributor to the model. And then after the period I've talked about, I started getting interested in ice sheet and glacier modeling. And at first I was just going to be sort of a sidelight in addition to the sea ice modeling, but it got to be more and more time consuming until after a while I wasn't doing much sea ice modeling anymore. And if Elizabeth was ever annoyed at me for straying and not being such a reliable co-author anymore, she never showed it, but just was very supportive that I'd found this new outlet for creativity and curiosity. And to be honest, I kind of wanted to be a lead author of something because I wanted to follow in Elizabeth's footsteps. And I soon discovered that the skill set of being a lead author is totally different and bigger than being a co-author. But I've really enjoyed that too. And then some years later, when I had the opportunity to come here, Elizabeth was also really supportive of the opportunity that I've had here. So for so many things, thank you so much.
That's great. That was a fun workshop. Actually, what I remember mostly is Julie Schrem's presentation at that meeting, because you kept talking about baking pies, and I just that was a presentation that really stuck with me. So anyway, so thank you, Bill.
Yep.
And our next speaker is Marika Holland.
Oh, it's cute.
We are running a little bit late, but I think it's fine. We'll just continue with Marika into the break a bit, and we'll take a break after her talk. This
one?
next is advanced.
Oh, this one.
Yeah.
I can't read without my glasses. So. So I've had the privilege to work with Elizabeth for I think it's about 25 years now. And actually the first thing I did when I became a postdoc, and I'm not going to actually talk about this any more than right now, is I contacted Elizabeth and asked for the elastic viscous plastic model and embedded it into the UVic climate model. And the code was so incredibly easy to use and work with that I think I had it in the UVic climate model within like a month. So so I'm going to talk about history that really is about the CCSM, which has now become the CESM. And so this is very much that perspective. And I appreciate there's many other perspectives, and some of which we've heard in the room. But this is the bulk of the work that I've done with Elizabeth over the years. So I started at NCAR in 1999 as a postdoc. And NCAR had the parallel climate model that you've heard about a little bit from other talks. There was also the climate system model, CSM1, which was released in 1996. Okay, and so this model, the sea ice component within that model had the three-layer Sumter thermodynamic. It had the cavitating fluid rheology. And it had something known as the Zamboni effect. This was just a kludge because you got areas of ice where when the ice converged, it got really thick. And so they just take that ice and just kind of spread it around across the Arctic. Anyway, not very physical, but yeah, so that's where things were when I started at NCAR in the context of what became the CCSM. And Elizabeth and I started collaborating around that time. CC as well, Bruce Brigley was here, Julie Schramm was here, and we were all sort of collaborating together. And Tony Craig was the head of the software engineering group here. So in 2002, CCSM2 was released, and the sea ice model was completely revamped. It included, as you've heard, the bits of Lipscomb thermodynamics. It included Elizabeth's EVP rheology. It included an ice thickness distribution developed by CC with Bill Lipscomb's linear remapping scheme. So it was a completely new sea ice model, a huge advance from where we'd been in 1996. And in recognition of this, Elizabeth and CC won the Distinguished Achievement Award. Now, you'll notice that the name changed. It was the CSM1. It became the CCSM2. And that's because we added community into the name. And that was in recognition of the fact that the community, not just people at NCAR, were helping develop this model. And the sea ice component of CCSM, what's now CESM, is a huge example of this. We've relied on the broader research community to build this model, to use this model, to do fun things with this model. So there was a technical note written about the sea ice simulation from this model. Bruce Brigley led that. Unfortunately, Bruce isn't here. We tried to contact him and find him, and he's still here on this earth, but he's not here in this room. Sorry, CC looked really concerned for a second. But anyway, but CC, Elizabeth, myself, Julie, Bruce, and Dick Moritz, who also was very actively involved at that time. And we did interesting science with this model. So we did a lot of cool things. People were using this model for different science. So for example, we looked at the mechanisms forcing an Antarctic dipole in sea ice conditions. And this was a collaboration between myself and CC and Elizabeth. So we were looking at this first EOF of sea ice concentration, which looks very similar to the observations, and what drove that in the model. We were looking at things like the advective nature of those anomalies. So this shows a correlation map, so function of longitude along the x-axis and lag along the y-axis, showing that these patterns of sea ice were advecting around the continent. This has actually influenced my research to this day on things like predictability of sea ice in the Antarctic. So we are using this model to do a lot of interesting climate science and try to understand sea ice in the system. In 2004, the CCSM3 was released. And again, Elizabeth's fingerprints are all over this model. There was a new advection scheme that Bill Lipscomb and Elizabeth had developed, the remapping advection. There was some improved coupling. I think Cece was involved in that. She's not sure, but I'm sure she was. And anyway, so, you know, it was just a couple years after CCSM2, but still improvements were happening pretty fast and furious in the sea ice model. And again, we use this model to do and think about interesting questions. So this is some work again with Elizabeth and Cece and Bill Lipscomb and Julie Schramm, where we looked at the influence of the sea ice thickness distribution that's resolving sea ice and its high spatial heterogeneity that had been developed and incorporated into the model, and how that influenced the climate system, how it affected the mean sea ice state, how it affected atmosphere and ocean conditions and the coupling between these different elements of the system, and also how it affected feedbacks. And so the plot shown here on the right is actually a measure of the surface albedo feedback as a function of the ice thickness in the Arctic from different simulations. And basically what we showed is that incorporating a sea ice thickness distribution led to a stronger surface albedo feedback. It affected the transient sea ice evolution and would in turn affect our predictions into the future. So there was quite a bit of a time gap between CCSM and CCSM4, about 6 years. There were some major improvements, again, in the sea ice model that went into the CCSM4. Along with the CCSM4, the CESM1 was released. So that was the Community Earth System model. Those models had the same sea ice component. They had the same physical climate model, but the CESM1 had biogeochemistry, a carbon cycle, and chemistry in the atmosphere as well. So the sea ice model had a new radiative transfer scheme, the Delta-Eddington scheme that people have mentioned earlier, that Bruce Bergleb and Bonnie Light developed. It also, in incorporating that scheme, which relied on inherent optical properties, it meant that we could do interesting things with aerosol deposition on the sea ice, ponds in the sea ice system. And so we improved those elements and how they interacted with the radiative transfer. And again, Elizabeth was involved in all of this work. And so we could look at things like, how do ponds change in a warming climate? How does aerosol deposition on the sea ice affect the shortwave radiative forcing? How are those things changing as the sea ice evolves? And so these figures here are just showing ponds on the bottom, aerosols on the top, and the shortwave radiative forcing associated with those things, showing that as a function of month here along the x-axis, the strength of radiative forcing associated with ponds was increasing over the 20th century as you could get more ponding on the sea ice. Aerosol deposition and the impacts of aerosol deposition on the shortwave radiative forcing was also shifting earlier in the season. That was because of when snowmelt was happening. And again, this was collaborative work involving Elizabeth Hunke. And you can see new names showing up here, like Dave Bailey and Bonnie Light as well, of course. So Elizabeth was instrumental in the sea ice modeling we were doing here. And we wouldn't have the sea ice model and the really cool things we could do with this model in terms of addressing polar science questions without Elizabeth's enormous contributions. But I also want to acknowledge that Elizabeth was also incredibly involved in the leadership of this project. And this was due to her service as a co-chair for the Polar Climate Working Group, which she informed me at lunch, started in 1999. Oh my goodness. I knew when she stepped down. I didn't know when she started. I mean, I knew you were co-chair with Dick Moritz, and then with myself, and then with Jen Kay. So Elizabeth might be one of the longest serving co-chairs of the CCSM model. She stepped down in 2014, but that was not when she stopped contributing to the leadership of this project. In 2015, she became a member of the advisory board. And she's chaired that advisory board since 2021 and still chairs that advisory board. And you guys are meeting in like a month or something. So yeah, so she has contributed to this project in so many ways. I also want to note that the SEIS Consortium, which of course has been incredibly valuable to all of this, was formed in 2016 when a group of us came together and realized that we really needed to formalize that this was a community model. And Elizabeth has led that consortium so incredibly well since it was founded. So CESM2 was released in 2018. It included the mushy layer thermodynamics that we've heard about, that CC mentioned you can do really cool science with. It included an update to the pond scheme that Elizabeth had led the development of. And so again, you know, Elizabeth is still contributing to the model in CESM. And that's true towards CESM3 as well, where, you know, we're taking advantage of new developments in SEIS, some of which Elizabeth has been directly involved in, and others which she's enabled because she's allowed this amazing framework for the entire community to contribute to this model. So I just want to say her leadership has really fostered this incredibly collaborative and collegial sea ice modeling community, and we all owe her an enormous debt of gratitude. And I'm not stopping here. I feel like that was a natural place to stop, but I'm not going to stop. Anyway, I just want to note that not all the ice has been virtual. I've also had the opportunity to tromp around on the sea ice with Elizabeth. And so we co-organized this Snow on Sea Ice Camp with Don Perovich in 2015. And then a year later, there was the Sea Ice Summer Camp in 2016. And so you can see photos of Elizabeth from that kind of sea ice camp, which just took place outside of Utqiagvik with her ice core baby there. And I also just want to note, it hasn't all been about sea ice. So you can see Elizabeth working hard here while myself and Melinda and Walt and Don think really deep thoughts or pretend to think really deep thoughts. We're really actually thinking about these snacks right here. And, you know, these people have taught me that it's not just about sea ice. It is about the snacks, and it's about deep thoughts, and it's about coffee. There you see some coffee. And it's about camaraderie. But if Don's around, it's mostly about the snacks. So, you know. And even when it's been about sea ice, it hasn't just been about sea ice. So like this Future of Sea Ice Modeling workshop, which took place in Iceland in 2019. And I had the opportunity to wander around the Icelandic landscape with Cece and Elizabeth and our sea ice groupie, Steve. And, you know, a lot of it is also about the friendships and the time together. And that was true recently when we were all in Cambridge together. And this workshop that Danny Feltham had organized at the Isaac Newton Institute actually got delayed by a day because of Queen Elizabeth II's funeral. And so we spent that day, Elizabeth, Cece, Bruno Tremblay, and myself, we spent that day wandering around Cambridge and the Cambridge Press. Sometimes it's also about opinions on Queen Elizabeth II's funeral. So we wandered into a church, and the funeral was being broadcast there. And the Cambridge News, the local press, could see that Elizabeth and Cecilia, the wisdom, their feelings and, you know, just how distraught they were about the Queen's funeral, and they interviewed them. This is actually from the paper, by the way. They didn't interview myself or Bruno, so apparently, you know, they knew who to talk to. So I've been privileged to spend basically my entire career collaborating with Elizabeth. And when I started collaborating with Elizabeth in the late 1990s, this is the sea ice and what it looked like. We're using these models we were building to project and predict that the sea ice cover would decline. We were seeing little bits of that, but mostly there's a lot of variability from one year to the next. In the course of my career, our careers, we've seen what we were predicting. The sea ice cover has declined dramatically. We're in a totally different state now, and we project this to continue. And as Andrew said, you know, reaching near ice-free conditions in the not too distant future. So just some closing thoughts. Elizabeth has really led the sea ice modeling community in the US and globally, I'd argue as well, since the 1990s, the late 1990s. And this has resulted in an incredibly good model, a really sophisticated model that includes so many different processes, allows us to address so many different questions, and it has enabled a huge amount of science, both by Elizabeth, but by many of us in this room, and many, many more outside this room. An entire community has benefited from Elizabeth's leadership. I think as important, or maybe part of why that science has been so successful, is that Elizabeth has also led and fostered a community. And without her, we would not be the community that we are. And so I'm going to get weepy because I do that anyway. But I think Andrew alluded to this also. It's made all of our science richer. It's made it more complete. It's made it more collaborative, and it's made it a hell of a lot more fun too. So I'm just incredibly grateful for all the years of collaboration and friendship, and I look forward to many more adventures in the years to come. So thanks.
Good timing, Dave.
So now we're gonna have a break.
I think we're next. Yeah, hey there, can y'all hear us?
Yeah.
Hey, good.
Yeah, I think it's the Naval Research Labs show now.
Great. Well, are we okay if we?
Oh, you're all in the same room even.
Yeah,
That's
we're not, yeah,
awesome.
that's right. Yeah.
Oh.
We're at NCAR South. That's right.
Oh my God. Yeah. I think we were in that room.
All right, well, take it away.
All right, we got it.
We have a group from the Naval Research Lab that are going to present their thoughts.
Okay, so you ready for us?
We want to go to slide 2.
Already.
Okay, so this is Ruth Preller speaking, and I'm just going to talk a little bit about how we got into this business and then met Elizabeth. And before I start, I want to make sure that I say this, and that is, I want to congratulate Elizabeth on really an outstanding and productive career. It's been just wonderful working with you, Elizabeth, and I wish you and your husband all the best in a well-deserved retirement. And just remember, Elizabeth, you have my personal email, so please email me. Okay, so to start off with, the Navy began to be interested in sea ice prediction in 1984. And they asked me to take that project on, and I was lucky enough to be able to hire Pam Posey to work with me. And what we did initially was we actually went to work or went to Krell and worked with Bill Hibbler and Terry Tucker and got the Hibbler sea ice model, brought it back to the Navy, and worked to set up a version of the Hibbler ice model with monthly mean climatological ocean fields underneath it, and driven by the Navy's atmospheric model, which I think was no gaps at that time, I can't remember. And we were able to set up something that we call PIPS 1.0 in 1987. And that model, we thought we were doing really well because that model had 127 kilometer resolution. And it included the Arctic Basin and the Greenland and the Barents Seas. But then they asked us if we would do some higher resolution solutions in the Greenland and the Barents. So we set up a similar model one for each of those areas at 25-kilometer resolution. And I will say that when we started working on this, I thought we were in kind of a unique position because the rest of the academic community was also running ICE models, but they were running the models more to look at interannual variability. So they were doing long-term runs, whereas the Navy wanted us to provide them with a 5 to 7 day forecast of sea ice, in particular the ice edge location and movement. So we had sort of a different problem that we had to look at. So we had our kind of course resolution Hibbler ice model that we had in the 1980s, and then in the 1990s we began to work on a coupled ice ocean model using the Hibbler and the Cox model coupled together. We also decided that to try to assist in our actual 5-day forecast, we would initialize it from DMSP SSMI data, some ice concentration data from satellites. So that was our initialization field. And in 1996, we actually set up a model operationally. That was our PIPS 2.0 model that had 27-kilometer resolution for the entire Arctic. And I think you can see on the slide what the domain of that model was with 15 vertical layers. So that was 1996. Well, it did reasonably well, but we realized that we needed to have better representation of the ice thickness and get a better solution for both the growth and decay of sea ice and our ice motion. And it was in 1996 where basically I met Elizabeth. Steve Piachik, who was one of our scientists here, invited Elizabeth to come out and spend the summer with us in 1996. And she was already, I think, working on her EVP code, excuse me, at that point in time. But that's how we began our relationship with Elizabeth. And it's been a truly, productive and wonderful relationship throughout the years. But that's sort of our precursor up to the sea ice model, or I'm sorry, the SICE model, as we heard earlier today. And Pam, if there's anything I left out of that little history that you want to add, because otherwise I'm going to let Rick and David take over the more recent work that was actually using Elizabeth's model.
Yeah, so in the 2000s, we switched from PIPS 2, this is Pam Posey, I'm sorry. In the 2000s, we switched from the Hibbler ocean model and started using, like Ruth said, the sea ice model. And I'm old school, and an old dog is hard to retrain. So sea ice forever for me. SICE just, I know I should use that terminology, but I just don't. So sorry, guys, up front. But we started working with the implementing Elizabeth's sea ice model into our into a more up-to-date ocean model, which we call HICOM. That resolution is 3.5 kilometers. In the ocean model, we had 32 and then later 41 vertical layers. And you can see an example of ice thickness on the right. And that model ran operationally from 2006 until the early 2010s. So it had a good run and produced forecasts that the Navy uses. And most of our forecasts went to the National Ice Center, which we have a strong support group there that uses the model forecasts for many different aspects. And then, David, do you want to pick up after that from the 2010 zone?
Yes.
Maybe Rick?
Yeah, well, I've got other slides that talk more about the more recent stuff. So I think we can stop here. But if we go to the next slide, we have one slide about the Arctic cap. And Pam was involved with that with Joe Metzger, and we had a close collaboration with the Weather Service office in Anchorage with Carvin Scott. And so, Pam, if you can dust off those cobwebs and what you remember, this is a big deal because the Arctic Cap is just about to go operational in 2012.
Yeah, and they came to us and asked if we could forecast. They forecast the ice conditions because we had the Coast Guard cutter Healy that was going to make a run up to Nome, Alaska, and so they needed to figure out a good direct path for the Healy, the most efficient way for the Healy to make it to Nome, Alaska, and our Arctic Cap Nowcast forecast system was actually used, which has at the base of it the sea ice model, and it was used for the Healy to go into Nome, Alaska, and this was really important to know because it was a resupply mission, so it had fuel on board, and they had to know how closely they could get to the coast for them to pump off the fuel into Nome area. So this got a lot of press for us, and it was the forecast worked really well, and we were really proud of this, is what I remember. Now that's from 2012, and I've been retired for 7 years now, so the cobwebs are really hard to shake off.
You're good. Thanks,
So-
Pam. So we'll go to the next slide, and this is, we'll let David talk a little bit. This is when he first knowingly, I think, met Elizabeth.
Yeah, so that's right. So we first met at the summer school here. That was up in Fairbanks. And we were talking about melt ponds. And I think, in fact, Marika mentioned this melt pond, the level melt ponds that Elizabeth was working on. So I was fortunate enough to talk with her and help with running a lot of the tests for this to help bring about this publication for the level melt pond scheme that's in the SICE model now.
So we don't have a whole lot of slides, but I'm trying to go in chronological order. So at one point, are we showing that or are they showing it?
I don't think they're going to see this.
Yeah,
The
they're
next slide, you don't see a slide with
No, they don't.
with a small plane
Yeah.
picture, right? So yeah.
So I don't remember when, but sometime in the mid-2010s, Pam was still working with us. And then Elizabeth and Steve were, I think, visiting maybe one of his parents in either Kentucky or Tennessee. And they had their small plane, and they reached out to Pam and talked about stopping at our Stennis Airport, which is really close to where we worked. And so what we did is Pam and Dave and I, we met them at the little airport, and we went out for lunch at a place called Dempsey's, which you don't have the slide showing this. And then we had a nice meal, and then we drove them back to the airport. They got on their plane, and they were, I think, eventually heading to Los Alamos, but they were going to fly maybe, I don't know, Houston, somewhere in Texas, I think was their starting point. So that was kind of fun. And now we'll move to the next slide. So this is more recent history. So this is where we had our first workshop in Boulder. Many of you were involved with that. And this is a nice photo. NRL policy is I can only show a photo, either I identify all the people in the picture or it's on the web. And luckily, this one was on the web. That was our last real meeting before COVID. So this is February of 2020. And it was a great opportunity to get together with some of the younger researchers. So now we will go to the next slide. I'm just going to talk a little bit about our Earth system prediction capability. So it's got the Navy's atmospheric model, HICOM with tides. We've got SICE version 6 in it, and then we have WaveWatch 3. And I won't go into details, but this system, the deterministic, was transitioned in late August of 2024. It has the capability to produce a 16-day forecast daily, but due to the operational cores available right now on our supercomputers. It's running an 8-day forecast, which is still an improvement over the Goff's system, which was run up to 7 days. And then we'll go to the next slide, and this is a little bit more, give you a little more technical details of our various systems. So we had an ensemble system which went operational in August of 2020, and it was run weekly, producing a 45-day forecast. And that was with SICE 4. The computer that was run on was an SGI that went away. They're in the process of getting this running on one of our newer platforms. The deterministic, you're seeing the different resolutions. The atmosphere is at 19 kilometers. Our ice and ocean model, they're at a 125th degree. So that's 1.75 kilometers at the pole. And this includes the landfast ice parameterization that Jean-Francois introduced based on his 2015, 2016 papers. And we're working on transitioning our version 2 ensemble system. And anyway, that's all I'll say on that. And this is an example of our ensemble forecast system, which is not running right now. The next version will be, but this is in anticipation of the ICEX. So this is from early,
21.
this is late October of 2021, and the ICEXs are in even years. So there was a buoy, and so the black line shows you the mean of the ensemble forecast. Is that right? No. There's a darker red line, which even I can't see well, which is the ensemble mean, and you're looking at the trajectory of the buoy. And basically you can see with this 45-day forecast, it did a reasonable job of showing the transit toward the west-northwest with some variability. And on the right, this is one of the products that Pam and contractor Julie Kraut worked with the NIC to make a flat product, Partridge Leads and Polinius, and it's basically looking at strain rates. And so during ICEX, the NIC would put this product out to give a sense for what one could expect over the next 5 days. And is that it? Yeah, and there's more recently, we had our consortium workshop. I know I saw the photo from that earlier, which unfortunately I can't show because I can't identify all the people in the picture. But, that was a great opportunity to get everybody together, and we worked hard with the tutorials. And, I want to give Tony Craig credit because he's just an amazing person who knows that code inside and out. And I think Elizabeth know that we she announced to a few of us in May that she was going to retire in February this year. She probably took a pretty good time. And that's all I will say. Is there anything else? Did I miss anything? Pam or David?
So I wanted to say, Elizabeth, I want to echo Ruth's words about what a tremendous help you've been to us over the years. When I retired 7 years ago, I thought that the stars had aligned because I was 56 years old and I had 30 years of federal service. So I thought, okay, stars have aligned. But Elizabeth, you have trumped us because stars are not aligning today, but the planets are aligning today. So I think it's very fitting that we're having your retirement seminar today. We wish you the best of luck. We're very proud. You've had a wonderful career, but you also, we're very proud that you get to sit back and enjoy the things that bring you pleasure. And we hope that you do. From NRL down here, we appreciate and thank you very much. Thanks, guys.
Yes, thank you.
Thank
Yes.
you.
That was just wonderful. I want to also acknowledge and thank you for all of your contributions back to the consortium, especially in the testing and infrastructure area and stuff like that. It's just, you've been such a valuable resource there. So are there any questions or comments for the folks from NRL? Okay, well, thanks so much. So, and sort of continuing in the consortium theme, Alice Duvivier is going to speak, even though she's not actively working with the consortium any longer, but she was very critical to some of the initial parts of the consortium. So with that, I'll let Alice take over.
All right. So for anyone I don't know, I am Alice Duvivier. As Dave said, I will touch on the consortium here, but it's not a talk entirely about consortium. And like Aaron, I cannot be the one in the room who says I've known Elizabeth the longest. But one of the things I noticed when Dave and Marika and I were organizing some of this was that Elizabeth had, some ideas of people who she maybe wanted to invite, and a lot of them were her mentors or people who had helped her early in her career. But that kind of left out those of us who were younger, who for us, she helped us really start to understand sea ice and start our sea ice career. So in this sense, I'm going to talk about my journey to sea ice and how I've related to it and this idea of consorting with giants. And I have used, I'm not a good artist in any way, shape, or form. So I turned to ChatGPT to help me to create some images. I've credited them all, but some of them are kind of comical. And this is the first one. When I went to ChatGPT and I was like, draw me some sea ice giants in the ocean, this is the kind of thing that it produced. And maybe this is me down here. And I decided Elizabeth should have that big crown. It was actually surprisingly hard. I said like 3 women things and it kept giving me all men giants. So that was a little bit frustrating. But anyway, this is what ChatGPT thinks a sea ice giant looks like. So Elizabeth, you can choose which one you are. You don't have to have the crown, but if you want it, you can have it. All right, so I think many of you know this, but I wasn't ever officially trained as a sea ice scientist per se. I've never taken like a sea ice dynamics class or a sea ice thermodynamics class or anything like that. So sometimes I feel like this little Adelie penguin on the ice with all these different tracks, kind of like, what am I doing here and where are my buddies? And but that's not really how my journey in sea ice has been. So my first investigations with sea ice was as an atmospheric modeler, and this was with the Regional Arctic System Model. So when I was in graduate school, in addition to doing my graduate work, I was a professional research assistant doing the atmospheric model development for RASM. And as part of this, I worked a lot with Andrew Roberts, and there are, of course, many more people who worked on RASM, but I'm highlighting him as one of the sea ice people. And Andrew, I didn't have a better picture of you, so this is the one you get. Yeah, it's at the sea ice camp. And as part of the atmospheric modeler, I will honestly, a lot of times I felt like, what in the world am I doing? How can I really do this? But I worked with Andrew a lot on trying to understand what was going on in RASM, if it was actually coupling correctly and doing what it should be doing. And so I did this all from the WRF atmosphere side primarily, but we worked together on looking at some of the exchanges of heat fluxes over land and sea ice. We had a bias where we were getting a lot of decoupling over land, but we were also concerned what was going on over sea ice. And this led to some changes that we had where we realized we weren't passing both the fluxes and the exchange coefficients or stability that we needed, so that both models thought they were doing the same thing, and so they weren't really evolving properly. And so I remember many conversations between Andrew and I think back then we called them telecons instead of Zoom meetings. But we'd have lots of telecons about what was going on. We also had some of these same issues. This is just a NC view of some of the RASM output, but trying to figure out like what's going on with the albedo. In this case, the sea ice albedo actually looks pretty good in the center of the figure, but we had some weird stuff happening with the ocean, and like when the sun was down, we had an albedo of 1. And anyway, there are lots of these little things. But because of my work with RASM, we had twice annual meetings. And the first time I actually met Elizabeth was at one of these meetings. I don't know that she remembers this at all, but I remember that Andrew introduced us. And again, I went to ChatGPT because I have no pictures of this time. And I asked them to say nervous graduate student meeting male and female mentors. Again, it defaulted to a man, so I had to specify female graduate student. And this is what it thought that should look like. So you can decide if this looks like Elizabeth and Andrew and me. But this is ChatGPT's thing. I just remember being introduced and kind of feeling like, oh, I know you're a really important, like, significant sea ice modeler, and I don't know what I'm doing, and I'm a grad student. So that was a little bit how I felt with that meeting. But this is before I had a smartphone, so I don't have any actual pictures of that meeting, I learned. So this was all virtual sea ice interactions. The first time I actually saw sea ice was again during graduate school. I got to go to Antarctica and I was installing weather stations. So still atmospheric science, but we got to fly over the sea ice sometimes. And I thought it was super cool to see the edge of the sea ice. Of course, it was summer there. But just like you can see how quickly you go from open ocean to ice pack and looking at the different flows. And I thought that was super fascinating. So that was in 2012. And for the rest of my PhD, I continued to work with modeling from the atmosphere side. It was all interactions with sea ice virtually, but I looked into what was happening with heat fluxes over sea ice and over open ocean, and found that in WRF, they had some really crazy assumption that sea ice should always be 3 meters thick, no matter the season or anything. And this led to some kind of wacky heat fluxes that we were finding. So that was one of the things I worked on then. And then using RASM, I was able to, where we have a variable sea ice concentration and thickness, we were able to look at heat fluxes over sea ice in the ocean and try to understand with different wind conditions how that would affect like mixing in the open ocean. So that was all graduate school. And I graduated in 2015, which I realize is like 10 years now, which feels very bizarre to me. But my first introduction to kind of the wider sea ice community was that I somehow amazingly got invited to this sea ice camp that Marika mentioned. And I don't actually know how I got invited, because I feel like I look at this and it's a bunch of sea ice people, and then there's me who's like this atmospheric modeler who does polar stuff, but not really sea ice. But I thought this was really great. So this is the whole group, and then me with my little team. I was on CC's team. And so I think, throughout my whole career, I've been able to interact with some of the sea ice giants, not just Elizabeth. We weren't on the same team, so we didn't get to go out and measure thickness together. But I think this was my first introduction to how welcoming and kind the whole community is. And so this was really pivotal for me, honestly, as a scientist that was like, I really enjoy this community and I'd like to be able to do more with them. And so I think that this was really, really important for my career. While going through pictures, I didn't have any great ones of just Elizabeth at the camp other than the one of her holding her ice baby. But I also just saw this one of Ed Blanchard Wrigglesworth, and he was kind of like an ice giant. So, Laura comes up to like his shoulder. So both metaphorically and literally, maybe this is the case for him. So in summer of 2016, I came to NCAR and started a postdoc, and I wasn't really doing sea ice yet. I was doing more ocean modeling. So I did some Southern Ocean mixing work, but I was still well north of the sea ice zone. And it wasn't until 2017 when I was officially kind of a sea ice scientist, when I got hired to work with the SICE consortium setting it up. And so primarily I worked with Elizabeth and Tony and Dave and Marika to, and of course the rest of the consortium, but I would say most of my emails back and forth were with this group. And so I did a lot with helping set up the original GitHub repositories and the documentation. And we ran town halls at AGU, and we wrote about the SICE consortium. And I learned Elizabeth grew up in Alaska. I Googled that. I couldn't find any pictures of Elizabeth Hunke, Alaska, anything like that. I didn't ask ChatGPT to help there either, sorry. So that was a lot of what I did. That wasn't as much science, but just kind of the logistics of actually getting the consortium up and running, and how were we gonna make people do PRs, and what did this look like? And then in February of 2020, we had the first SICE consortium tutorial and workshop that was here in Boulder. The whole group is on the left. I don't have the same rules that Rick does, but I think these might be on the internet at large anyway. And then the organizing group was up on the right. And the day of the consortium, it was like perfect winter weather for February, and it snowed like 6 inches. And you can see these bears that were at my daughter's school, and they had these snow mullets, and I thought they were fantastic. So I really liked this weather, but I don't think everyone else, I think many of the people who came liked it, but I remember being concerned that we would, like the building would be closed and everything would be for naught. And then just like a month later, everything got all wacky and COVID hit. And so I spent a couple of years where this was kind of my work environment. You can see my daughters are there, and then a friend of my daughter is there as well. But my office is like in the living room, and my daughter with, I think she has butterfly wings and cowboy boots and like a 4th of July dress and a helmet. I don't know why all of that's together. But anyway, they got to watch me do a lot of this research. And I think this is actually really good. They still pop in on meetings. If you're ever on meetings with me, they sometimes come in and make faces and sometimes wave to some of you guys if they know you. But I think being able to see them to see me doing science and work was kind of influential for them. And I also felt really supported during this time because it was like absolute chaos and school shut down. It was like, how are we going to do anything? And I had this email chain that I looked up. It was just with Elizabeth and Tony about the COVID situation. And I just want to point out that it wasn't really about work per se, but it was more about like how to get through this and how to have support. And so like Elizabeth's email on the top is like, we have to take care of ourselves and our families first, you know, have your own expectations psychologically, like we're in good shape, don't worry about it. And the same thing from Tony, like look after yourself, make time for yourself. And so this helped me a lot during this crazy time when I felt like, you know, the CIS community, again, it's reinforcing what I first experienced in 2016, but where it's kind of like a family and it's really welcoming and supportive. And it's not just about like, well, you didn't get this work done right away, because I was working at all sorts of crazy hours during that time, as probably many of you guys were too. Like when I wasn't trying to facilitate my kids' school and stuff like that. But it was like they care about you as a person, and that was really influential for me too. And so I've been able to continue. This past May, I went to the second SICE Consortium tutorial and workshop, which was in Santa Fe. And I think it was great just to see some of these people. I hadn't actually seen them in person since 2020. So it was really nice just to see everybody learn more about the model, because I haven't been as hands-on with the consortium work lately. And in the interim, I've been doing other stuff like I have done more research actually with sea ice, looking at the thermodynamics and the impact on the coupled system, and giving the model tutorial at the CESM. And it's very humbling and odd to think like, oh, I am an expert in this. So I think at some point you feel like there are adults in the room who know what's going on. And like, then at some point people are treating you like the adult in the room, and you're like, am I really the adult in the room? Like, I don't know if that's true. And throughout this, there's still been the same community, whether it's through the consortium or also through the Polar Climate Working Group. So some of you were attending and everyone was invited to the weekend up at Snow Mountain Ranch, but we've kind of informally the past 2 years had these coordinated Snow Mountain Ranch like cross-country ski days. And so these are some of them where it's just like, it really feels like you're part of a group who does great science, but also wants to hang out and be together. And so I would still say I'm a polar system scientist. I'm not exactly a CI scientist. This is what ChatGPT thought that looked like. I asked it for seals, and I don't know what those animals are, but they're a little bit more wombat-y. Yeah.
Did you put in polar system scientist and it gave you a woman?
No, this isn't the full thing. It was like, that was a great question. Polar system scientists with ice flows and ocean and wind. And then it was like a female scientist and seals on the ice flow. And then it like did something. I was like, do you want me to change this? And I'd be like, yes, please make her face not creepy. Something like that. This one's face is not as creepy. So yeah, I still feel like I'm a system scientist. I don't know if I'm exactly a CI scientist, but I always do polar stuff, and I feel like everything's connected there. So it's really important to understand how the sea ice is working. And I've lately more shifted to understanding biogeochemistry as well as the physical system. But sea ice has always been really central to all this work that I've done. So I don't really feel like I'm this lone penguin on the ice, but that I can rely on my whole sea ice community, and we're kind of huddling together and making sure we all stay warm and don't freeze together. So thank you to Elizabeth and Marika and Dave and Cece and Andrew and all the people who I've worked with a lot. I think all of you feel like giants to me. And so I'm really grateful that I've been able to be part of the community.
Any questions or comments?
Comments for Alice? Okay. Thanks, Alice. That was great. So our last official speaker of the session, continuing on the RASM theme, we have the one and only Wisław Maslowski. So.
Okay. Can you hear me now?
Yep.
Okay. I think that I'm one of the people that can claim that have known Elizabeth for as long as it takes. We coordinated in the morning, and I think that we met first time was a little bit either 1994 or 95, around that time frame. One of the earlier CHOMP meetings probably, or something like that. And I'll be talking about the regional model, regional architect system model. And if it looks like I'm bragging, I apologize. But the way I thought about this presentation is that it's a success story with sea ice in the middle, okay? And Elizabeth is the person who has been basically in charge for all the improvements that we've got into this regional model with the sea ice component. We've benefited with getting updated versions every time updates have been available. Tony Craig is another person that I've known probably as long as Elizabeth or longer. So we have the access to the software part of it, and with RASM being couple climate model, commonly has been serving as the first fully realistic test of improvements in size and improvements with different parameterizations. So I looked at the first publication that I can claim that it's involving Elizabeth and anybody from NPS, and that's the paper that Elizabeth and Yusha published together back in 1999. And the paper title is has a high resolution in title. And that high resolution, if you look at the, somewhere I have information, this is the 18-kilometer model. So in 1990s, 18 kilometer was considered to be high resolution. The plots are showing difference in ice concentration and drift, comparison VP, the viscoplastic, and EVP that Elizabeth just published 2 years earlier. And she was in 1996 at NPS in person, visiting and working with Yusha in particular, under maybe some advice from Bert Sempner, who was our guru. And they got that paper together, basically demonstrating that EVP works as well or better than VP in relatively high resolution simulations. I think those were relatively short simulations, but still, if you look at the comparison at the bottom in terms of the difference in ice velocity, thickness, and concentration, it basically was a first ever demonstration that I think that later on convinced other people that this is a good model. Others should try it and adopt it and move on. So you've heard about RASM, and I'm very glad and thankful to people who already mentioned that RASM. Probably don't need to introduce much of that model, but one thing I wanted to point to you is that the domains are shown in the upper right panel. The schematics is shown in the lower right panel, and I just want to make sure that it's clear that it's a fully coupled regional model. It's like CSM. Actually, we took the pop and size from CSM, as well as the coupler CPL7 that Tony helped develop as part of the CSM as well. Later on, we added marine biogeochemistry with great help from Elizabeth again, from Nicole and other colleagues from Los Alamos. I just wanted also to mention that the first ever regional pop application, to my knowledge, was thanks to work with Elizabeth and Bill Lipscomb. We had to change some of the things with the pop in order to make it work in the regional sense with some restoring along the lateral boundary conditions. But I just wanted to bring this slide and basically say that we have a relatively high resolution sea ice, 9 kilometer or 2.4 kilometer in the ocean and sea ice, and we have a relatively high frequency coupling, and that model doesn't use any data simulation, doesn't do any bias correction, and it provides physically consistent initial conditions for forecasts, which I want to go and talk about this as the next slide. So basically, since 2019, part of the initiative that was the Sea Ice Prediction Network and Sea Ice Outlook, we started producing ensemble forecast every month from January 2019, and that's been going on, still ongoing. And I'm showing here an example of the size capability here, where we are running roughly 30 ensemble members, and the ensemble mean here is represented by the blue line. The spread among the ensemble members is represented by the shade, and the red dotted lines are ice extent from NSIDC. And this is a forecast initialized on April 1, 2024, and we're predicting September minimum 6 months into the future. And if you look at the numbers, maybe they're not the best, but as a matter of fact, it's without data simulation and without the bias correction. I would argue that that's a pretty good result. Again, what I'm trying to say here is that sea ice model and the rheology and the numerics works in such a way that we can do this type of application for subseasonal to intra-annual, what we call intra-annual 6 months into the future. And I'll show you some slides using the same application for decadal downscaling from the global models like CSM and E3SM. We're currently preparing a paper evaluating the forecast, but actually Mitch Bushwick published a paper last year where he evaluated, he was the lead author evaluating multiple models, qualifying the skill in September ice prediction from various dynamical models. And RASM was pretty well performing. The plot on the left is basically trying to do some more in terms of representing the skill of the forecast relative to the climatology, which is shown here by those 3 rows here. And we're looking at the color shading where the RMSD is quantified, and blue is good, red is bad. And you can see that most of the time compared to climatology, 6 to 1 month forecasts are beating 10, 20, and 30 year climatology with prediction of the sea ice extent in the Arctic focused on September. If you look at the comparison of the regional Arctic application with the sea ice model, size model, compared to CMIP6 models, which are all these color lines, and the RASM is shown here in blue, so it's not perfect. We have significant biases during the summertime, during the melt season, but you can clearly see that there's a huge improvement relative to the Earth system models, which are represented by the other color lines, where they have wintertime biases in excess of 1 million square kilometers and summertime biases maybe up to 3 million square kilometers. So the whole idea is that we are, again, not assimilating any data. We're not correcting biases in the model. We're looking at the performance of the size model in the fully coupled regional configuration. We can evaluate skill in terms of ice thickness distribution, which we believe that it's important, and the size model with the multiple category distribution with the improved thermodynamics, improved dynamics, and the EVP being part of it as well. As a matter of fact, if you look at and compare to PyOMAS, which does some data simulation, it's not performing worse. And if you compare Cryosat scatter plots between PyOMAS and the RASM, maybe actually it's a little better than PyOMAS with the data simulation. If we go and compare the change in rheology, so this is EVP versus EAP, anisotropic elastic plastic, there is a big change in terms of the scale of the forecast. There's not much change in terms of the rheology as measured by the ice extent. But if you start with a different ice thickness distribution or volume on the right panel in the lower corner there, that 6 months forecast is affected by the initial conditions subject to that different rheology. So an isotropic shown on the left, isotropic shown in the middle, and the big difference between the two for the initial conditions is shown on the right upper right panel, 0.5 meter throughout the whole Arctic. And if you look at the 6 months forecast on the lower right panel, is basically showing that difference of roughly 0.5 meter persists for up to 6 months in a forecast way. RASM can do because we do prescribe realistic lateral boundary conditions from the atmosphere, and in the upper half of the atmosphere, we expect this regional model with the sea ice to represent the sea ice events as observed from satellites. The panels on the right, 4 panels on the right, are showing the 2018 February and August Polinia from observations, the first 2 on the left, and from the simulation, where we're showing that not only the location, but also timing has been well represented. When you go to the wintertime simulation of the ice drift anomalies observed during the mosaic time period, showing the upper 2 panels on the right and the scatter plots on the bottom, the sea ice is performing well in terms of the drift, in terms of ice thickness distribution, in terms of those type of events like Polinias that are forced by simply atmospheric forcing from below in terms of Polinia in 2018 and both summer and winter. When you have a bias in the particular regions, such as, for example, Barents Sea, sometimes we see those biases. It's a matter not only how well your sea ice is performing, but also the forcing, and the forcing is definitely atmospheric forcing. This example is showing basically that if you have a very strong cyclone, like it was observed and published by Ed Blanchard-Wigglesworth in 2022 January, that huge storm system will actually remove in the middle of the winter all ice from the Barents Sea, and that's just basically ice redistribution. And it's nothing wrong that your model is actually underperforming or overestimating open water fraction in the Barents Sea. So the coupled system, when you have a good ice model, is actually giving you a reasonable results. The other thing that we've done, looked at, is that we're using NCEP forcing from the atmosphere to drive those 6 months forecasts. And we're showing here comparison for a particular ensemble simulation, April 1, 2017, initial conditions from what they used in CFSR, RASM, and then we're comparing against a mosaic estimation for the same period from Cryosat-2, and then September mean forecast of 2017 from CFSR, from RASM, with CFSR forcing in the atmosphere, and then we're looking at the Cryosat estimate. So distribution of the ice thickness in initial conditions and the forecast in size is actually quite well represented compared to the Cryosat-2 estimates. If you look at what the CFS is using, they have significant biases for initial conditions in the Beaufort Sea, and those initial conditions continue 6 months into, well, this is not 6 months, this is 6 months into the future as biases in the same location. We've used CSM DPLE for downscaling simulations up to a decade. And what we found is that if we're using initial conditions from a RASM, from the RASM hindcast, and we run it forward 10 years with atmospheric forcing from CSM model, we don't carry the biases that the CSM has in those decadal simulation, mainly because in the fully coupled configuration, we only force the large scale atmospheric forcing in the upper half of the atmosphere. The lower half of the atmosphere and the surface climate, including the sea ice, evolve independently according to the RASM physics and RASM behavior, and not carrying the biases from the global forcing data. We have the same situation when we try E3SM. This is the blue round represent the sea ice volume from the E3SM Arctic, where ice and ocean was refined to 10 kilometers in the Arctic, but the atmosphere is still low resolution simulation. Ice thickness from that run is shown in the upper right panel, panel B, and the RASM simulation downscaling atmospheric results is shown in the lower right. Basically, the biases that we have in the forcing, global forcing, are not carrying in the regional simulation, and the sea ice looks pretty reasonable on the initial conditions as well as on the forecast. So 10 years later, if you have initial conditions that are biased, you might have actually impact on the forecast. And I don't know how many of you are interested, but apparently the the forecasting beyond the synoptic timescale up to like decadal timescale is all like a gray hole for forecast, not only for sea ice, but for many other purposes. And there are a number of different communities looking at that particular timescale in terms of improving forecast and prediction and predictability. So finally, high resolution. I just wanted to say that if we go to higher and high resolution, you've heard from a number of people that a few kilometers model representation. This is a ice ocean model forced with a reanalysis at 2.3 kilometer in both cases. And we're showing the March for different decades and September from different decades. The purple line there, if you can see it, it's ice extent from the satellites. Yellow and black lines are estimates of the same ice extent in the model. So with the high resolution configuration for ice and ocean, we can further reduce biases that we've seen in the 9-kilometer simulation. And basically, possibly if we go to the fully coupled configuration with this kind of configuration for ice and ocean, we can see a dramatic improvement in terms of prediction and predictability. So I wanted to finish up basically saying that it's not just only sea ice or size and not only EVP, but I think that DOE's kind of strategy and philosophy in approaching the problem in climate modeling and prediction was combining the emphasis on the highly parallel codes with the talent of people that were hired to do that. And this applies not only to size, but also to POP. And now we have E3SM simulations that Andrew was showing, for example, focus on the sea ice, with a great promising that we can actually look at the sea ice in the Arctic or Southern Ocean and understand something rather than just only try to reduce biases. One thing that I wanted to say is that, especially again, addressing the concept of beyond synoptic prediction and predictability up to decadal, is that data simulation is not going to help you, because data simulation is just moving your model climate to some state which is artificial. And I think actually Marika some time ago, I remember, presented paper from results from CSM with trying to initialize ice thickness distribution, and the CSM within a month or so would go back to CSM biases as it was in the past. So what I'm trying to say here is that for improved prediction and predictability for sea ice, we think that improving the model fidelity instead of data simulation is the way forward, especially when we're trying to address this challenge of the beyond synoptic down to up to decadal simulations. I'm not going to read the other things, but I think that basically it is a success story from my point of view. We've had this benefit of collaborating with the LANL and DOE colleagues, and then NCAR as well, all the way going back to Bert Sempner, working with Bob Chervin here and Warren Washington, and then Bob Malone. And then the younger generation came in, including myself and Elizabeth and Bill Lipska and other. And I feel privileged that I had a chance to be part of that. And again, this is basically a way to demonstrate that the community effort works both ways. We take basically off-shelf development from size, and we implement it into a reasonable and focused regional model, and we can show how successful that could be. I'll stop here, and thank you very much.
Thanks. I fibbed a little bit earlier. We have one more official speaker, but before that, I'm going to say that we have an open mic sort of discussion session. So we will have the mics up ahead or up on the roof. And then if we could maybe just show all the online people, and if you have anything you want to say or jump in, it's just open. So who should we start out with? Peter Gent.
For those who don't know me, my name is Peter Gent. I've been a member of the oceanography section here at NCAR for a number of years. It's now 48 and a half, so it's a long time. There aren't that many of us around anymore who've been in the Community Climate System Model project for the whole of its history. This year we celebrate 30 years since the first version was put out. And Elizabeth wasn't quite in the project to start with. The first version of CSM didn't have a real sea ice model at all, but she has been in it since the second version. We immediately realized that we needed a decent sea ice model, and what else to use but EVP. That paper was Hunke and Dukowitz in 1997. And so I think I've known Elizabeth since probably the very late 1990s. I don't know whether you can remember what year you started working with us.
SM workshop in 1997.
Yep. So, okay. So it's been 27 or 28 years since I've known her. Now, I was the chief scientist of that project for 5 years. And as a couple other people in this room can testify, that job is like herding cats. But my experience was that the most well-behaved cat was the Polar Climate Working Group. They were always on time with their versions. They always produced nice models, and more important probably, they were always a pleasure to interact with. Elizabeth was a strong member and has been a really good member of that Polar Working Group, for that whole time since 97. You shouldn't underestimate the difficulty of and the work involved in producing a model which is going to go out public and that anybody can produce. Elizabeth, you should be proud at the number of other institutions that have taken up your sea ice model and have used it around the world. It's certainly been used in far more institutions than the CSM, for instance. That has been a huge amount of work, and you should be really proud of the effort you've put in personally to do that. Lastly, I've been retired now for a few years, so I can highly recommend being retired. They still let me in the building. I can still go to the cafeteria. I can still go for walks out on the mesa. And just occasionally, they listen to my opinion. You will be hopefully in the same position when you retire in a couple of weeks or months, it is. And as I said, I can highly recommend it. Congratulations on your career and your interactions with CSM. It has been a true pleasure.
Thanks, Peter. We have one online. Sure, Dave. I think you're muted.
Yep.
Okay.
So as an outsider, I very much enjoyed listening in on this community and getting an update on what it's doing. I'll be honest, the last paper of Elizabeth's I read was her paper with John. And that paper struck me as very good right away, but I had no idea at the time how good, simply because I didn't know the larger context of the community it was going into. It wasn't my expertise. When I was at Livermore, I was doing much higher temperature physics. And so I've learned from this, and I've heard good things about it ever since. But this meeting has been wonderful. A tribute to everything you've done, Elizabeth, and I've learned a lot from it. Thank you all, and thank you, Elizabeth.
Anyone else? Anyone else? Siobhan, are you on? I know you wanted to say something.
Yeah, hi Elizabeth. Apologies I couldn't be here all night. I did catch Bill Lipscomb's talk. I was also at that meeting in Victoria. That was the first time the two of us met. I also met Bill and Cecilia the following week. So as I said in the slides that I did prepare, but we didn't get to talk to today. But I met the two of you, the three of you in that first couple of weeks. But yes, the SAIS has been the basis of what we've been doing in Access for the last decade and a half. Obviously, along with the Met Office, who've also contributed a lot to what we've been doing. And again, was a major part of what we built up here in terms of the coupling, how we coupled it to the atmosphere was been a major help to how we built on. Because back in the 90s, we were using the cavitating fluid approach, which Marika described, and all the problems we had with that. But yes, it's been really good. It's been really good for Australia and how we're going forward. And how the work the slides I had a history of all the different models and all different approaches that we've been using and looking at the budgets and the like of the ICE, and I'll send you those slides on. But yes, it's been great collaborating. It's been great to know you. It's great how much the EVP has improved what we've been able to do in our work. And I again was one of these people I call myself semi-retired because I don't count myself as retired. I sort of work part-time and still supervise students and interact with the community and act as a mentor these days. And hopefully you'll be able to do that during your retirement. So you won't leave the community. You just won't feel quite as much responsibility for everything. Yeah, it's been great listening to the talks. I have been able to catch up, and I'll catch up with the rest on video. So best of luck for the future.
Yeah, come on down. Or you can just speak into the mic.
Okay. So for folks that don't know me, I'm out of my element here because I'm not a modeler. I'm a remote sensing observation person, but I've really enjoyed all the talks, and all the honor for Elizabeth was well deserved. I wanted to just very quickly point out one other area at least. I know Elizabeth best through our serving on the Cryosphere Working Group of the IASC, International Arctic Science Committee, I think. So that was, I think, started back in 2011, 10 or 11. Yeah, so they kind of reconstituted and started up these working groups, and we were the two U.S. Representatives to the Cryosphere Working Group, and that's helping international coordination for research. And Elizabeth and I contributed that, and particularly you, and it was enjoyable to work with you. And I just wanted to point out you're not just a modeler; you serve the wider Arctic science community as well. So.
Great, thanks. Oh yeah, sure. Thank you.
Hi everyone, my name is Jorge Urrego. So many of you may not know me. Some of you may remember me. So I did my PhD in Canada in ocean modeling. From there, Elizabeth took me as a postdoc in 2014. And I think coming to her group was in my short research career was a very good decision, the best decision I made. She was a superb supervisor, very open to explore ideas, help me with the code, when I was running large sensitivity studies. So she was very impactful from there. So I'm really grateful to have met her in my career. I have moved on from research since then, but again, thank you. I admire you very much. So happy to come here and see you again.
Mariellen?
Good afternoon. I'm Marianne Francois from Los Alamos National Lab. I'm the theoretical division leader, and I have known Elizabeth on my personal life because I share the same love of flying. So I've been flying on weekend with Elizabeth, and then later, this was around 2007 when we first met. Actually, it was at your house, I believe, for our one of the first meeting I joined. For a women's pilot flying organization called the 99s. That's on our personal life of what we like to do is flying. So we have this in common. And then I crossed paths with Elizabeth again when I became the deputy group leader of T3. T3, you had many talks from T3. Elizabeth has done all her career in T3. She is one of the pillars of the group T3, and she learned from the giants, I would say, from Demkovic and also Jerry Bragville. And then the baton was passed to Elizabeth. She even became a laboratory fellow. Congratulations again. And so that's T3 and all the background in numerical methods, fluid dynamics, solid mechanics. And now you heard this morning from Andrew Roberts and Erin Thomas that are also now taking the leadership in this area. So, and I see Bill, so it's good to see you, Bill. I was not here this morning. So this was between 2012 to 15. Then I went to do other things and came back as division leader in 2020. And that was good to see Elizabeth become a Lannel Fellow and continue her career. And she has done great things recently for the NNSA, some studies that we hope that will move forward with the future administration and the impact for global security. So we'll see where it goes. And sorry I could not be here this morning. And actually, it was a good timing that the meeting was here because I was at Warren Air Force Base yesterday and this morning. So and congratulations on retirement. And I look forward to more flying with you and Steve. So thank you.
Merci. The room. Anyone else online wants to say something? Jenny? I'm just poking at a few people. Okay.
I think I'm a little shy. Sorry.
Okay. Going once. Going twice. All right. Well, I'll take an opportunity to say a couple words. Oh, wait, there was one more. Okay. Jenny? Yeah.
No, I just wanted to say thank you to everyone. This has been really great. And it's been good to see some faces I haven't seen before. Thank you.
Yeah.
And congratulations on an amazing career, Elizabeth.
Great. Thanks. Okay. All right. I'm not seeing any others, but you're still welcome to jump in. But I'll take an opportunity to say, I think Elizabeth and I have a long history too. I think she came up to Boulder in 1998 or 99 or something like that, and part of the working groups. But you know, I was a graduate student down here at CU, and I wasn't really even working on CESM at the time. But you know, I just truly have appreciated working with her over the years on many things, just the CIS modeling part, but also developing the consortium and so many things along the way that have been just amazing. And what I really appreciate is Elizabeth taking my stupid questions. I mean, you always hear the expression, there's no such thing as a stupid question. Well, no, there is. But, Elizabeth's patience and just guidance and everything has been so helpful with me along the way. And so I truly congratulate you on everything and an amazing career, and I wish you the best. So, all right. Well, do you want to have the final word then? Okay. So I think you're.
Okay, I did put together a large deck of slides, which I'm not going to show. I'm saving those for Lannel, actually, because they have a lot of Lannel stuff in here. But from those slides, I picked out the ones that were really closely connected with NCAR and CSM, PCM, CCSM, CES. But those are just kind of a background, something for you to look at so that you're not looking at me while I go to thank so many people who've been important to my career. Okay, so how am I going to do this? Can I do it with the buttons?
Yeah, you can.
I can do it with buttons.
Yep.
Okay, so don't worry, I'm not going to go through my whole career in huge detail, but I have to acknowledge my undergraduate advisor for steering me into applied mathematics. Dr. John Haddock at Memphis State University taught me calculus. I didn't get that in high school. He taught me calculus, and he really did steer me toward applied math. I got assigned a report by an English teacher, and he said, you can make that a math paper. And it was on Malthusian population dynamics. So that was my first math paper. It was an English report, and I believe I got a B on it because the English teacher just didn't get it. So, oh well, but he liked it. He thought it was pretty good. But while I was at graduate school, or not graduate, while I was an undergraduate, I had a wonderful opportunity to go to Bell Laboratories for a summer and work with Julia Phillips, who eventually was at Sandia National Labs as one of the high-level managers. But she hired me to do computer modeling, actually just run a model, not build it, but run a computer model to try to understand the electrical properties of the interface between calcium fluoride and silicon. Okay, so she was looking for superconductors at this time. So this was in 1986, and that was my first paper. It was a computer modeling paper in Physical Research Letters. How rare is that? That was just like really cool. But the most important thing that I got out of that summer was a complete conviction that I wanted to work at a laboratory. I didn't want to work at a university. And Julia was just wonderful. And so I went on to graduate school, University of Arizona, and in the applied math program there. And the people to thank here are Dave Livermore and Mac Hyman, because they seriously did save my PhD. But what happened here, Mac came to visit the university from Los Alamos and gave a talk to the graduate students. And to be honest, I'd never heard of Los Alamos. I was from Tennessee. We never got past the Civil War in history. So I didn't know, but it was a laboratory. And so right after his talk, I marched up to him and said, Mac, can you take me on as a summer student? And he did, which was just amazing. How did he do that? But then later, John Dukowitz came to him because Mac had a lot of summer students. So John Dukowitz went to him and said, do you have a student who could build a sea ice model to go with POP? ocean program. And Max said, well, how about a postdoc? And so Max steered me into that job with John. So honestly, Mac is 100% responsible for my career at Los Alamos. So unfortunately, I don't think I've seen him on here. He was going to try to come, but he was on travel, so hard to make all that work. But he did give me the best advice of my career. And it was during this period in my PhD work when I was feeling really down because all this bad stuff had happened with my advisor and I didn't know what to do with my dissertation. And I just, and so what he said is, you don't have to be a Nobel winning scientist to have a successful science career. There are lots of different ways to contribute. I'm paraphrasing, but he basically said there's a lot of different ways to contribute. You don't have to be the scientist at the chalkboard who's writing equations with one hand and erasing them with the other while your pastoral graduate students are trying to take notes. And what he said is there's so many different ways to contribute. And I do remember him specifically saying, you can do things like synthesize information to make it more useful for other scientists. You can also organize people. There's all kinds of things that you can do to contribute to the scientific enterprise, even if you're not a, blue sky scientist, I'll call it that. And as it turns out, helping other people to reach their scientific goals has been my career. That's what I do, So it's not a control tower. It's actually the observation deck. That is the Atmospheric Sciences building. And they had an observation deck up there with windows all the way around. So you could watch the monsoon storms sail across the sky. And I mean, it was a fabulous place to have a desk. So yeah, I think I was really lucky to get a spot up there. You've seen this picture a few times. I am extremely grateful to Bob Malone for hiring me to work at LANL on sea ice with John Dukowitz. And the name SICE or sea ice has been mentioned a few times before. The reason that it got that name, when they hired me, I had never heard of sea ice. I didn't know what it was. Seriously. And they didn't mind that I didn't know what it was. I knew how to build a numerical model that could actually solve a homogeneous set of partial differential equations to show that, your hurricane's going to die, right? So I had the background that they were looking for. And so when I went to name the model, well, back up a little bit. When I told my friends what I was going to be doing at Los Alamos, I said, well, I'm going to be working on sea ice. And they were like, what's that? Is it this way? Sea ice, that's what they thought I was saying. And so that's why I named the model that. It was sea ice. It was for them. So John Dukowitz, he was my postdoc mentor, and he is the one who came up with the idea of adding elastic term to the viscous plastic equations for sea ice dynamics, because he understood already that that addition of that term was going to make the equations parallelizable, if I can say that. And I'm really grateful to him because I've always felt that project, the EVP project, was my real PhD project. That's where I really learned how to do things right, because I didn't get that in graduate school. And then Steve Ackley, down there, he took me to the Weddell Sea in Antarctica with the British Antarctic Survey, ROPEX. And just for a little bit of background, I think he mentioned it in his talk, but I'm not sure it came out. What we were looking for in the ocean observations there was the ice shelf water coming out from under the Filchner-Ronne ice shelf. And I came back to Los Alamos and said, hey, do you know there's ice shelves over the ocean? Can we put that in the model? And, Matt and Rick, and they were all like, nope. And that's running now. It's taken, what, 25 years to get that in, but with Bill's head start on that and the whole team, they finally did it. But one thing that the really important thing about this trip for me is that it started giving me my confidence back. You know, after graduate school, I was like, I'm not going to be able to be a scientist. And on this trip, it's like, oh, I can walk out on the ice. I can take ice cores. I can take data. I can synthesize that into a spreadsheet. You know, it really did start bringing my confidence back. And that was just, that was literally life-changing. Can't remember what's next on. Oops, was that right? That way. No. Okay, I'm gonna wait just a minute. In addition to Steve, Bert Sempner and Warren Washington's names have been mentioned several times in here. And oh my gosh, I'm so grateful to them, because talk about standing on the shoulders of giants, you know. They believed in me. They believed in my model. They said right out at the start, at this meeting that Vyacheslav was at in 1994, I'd only been at Los Alamos for maybe 2 months, maybe 3. They said, they said, you know, what Los Alamos is doing in ocean modeling, this is awesome. We want this. And I think Dave Bader said that that's where it started. The NCAR Los Alamos collaboration started with that meeting, with Bert Sempner and Warren Washington throwing their weight behind it. But they're more, because Dave Bader and Phil Jones, who is here this morning and is not here now, and Bob Malone were all so supportive. I was so lucky to not have to write a proposal for 20 years of my career. Can you believe that? It's not possible anymore. But they were willing to say, yeah, this needs to be done. We trust you to figure out what needs to be done. And they let me do it on my own time scale. They let me work with who I wanted to, on whatever I wanted to. And this is what happened. SAIS is what happened. And I am so fortunate for that. I don't know if I could do it in the current environment, but that was a great way to start. I didn't have any pictures of Bill because there's that gap between real camera and phone camera that just, you know, your wedding was right in there. I couldn't find any pictures. But anyway, Bill came to Los Alamos and was critical. I mean, I was, you know, even though I was working with the community, I wasn't really working with anybody day to day at Los Alamos. And then Bill came, and then we started trading off. He would do development and I would write a paper. And then he would write a paper on his developments while I did more developments. And we traded off like that for a long time. And I've always admired Bill for his expertise and for his thoughtfulness, your kindness, and for your incremental remapping in both horizontal advection and in thickness space for the ice thickness distribution, because that is hands down the most elegant part of the sea ice model. It has made so many things possible that we couldn't have done because the tracers were cheap. Steve's going to laugh at me for that because I always said in my time, tracers are cheap with incremental advection. And so we've been able to do all these new interesting approaches and capabilities like biogeochemistry and now waves, you know, that's because of Bill's work. So finally, I get to this picture, which has Cece in it. This is, you've seen some pictures from the Iceland workshop. We did have that fun day just wandering around in Iceland. But Cece worked with me to consolidate and clean up the sea ice model, that became SICE, and it became CSIM, the CICE model in CCSM. And I was showing Cece at the break in the notebook that's out there. I have a whole collection of emails that I had printed out from that period. And I printed it out for myself so that I could remember, because I have a horrible memory. But I wanted to be able to remember what our discussion was and what decisions we made and why we made them. But all of that is out there, and it's just remarkable. It was Cece and Tony and Marika and Julie Schramm and Bruce Briegleb, and I'm probably forgetting somebody, me. But that was the beginning of our community, I think. And so thank you to Cece for your willingness to compromise on that code, because we both had to compromise, and for sharing your CICE knowledge. And I think we made a pretty good team, even back then. I've also had a lot of indirect support from NCAR or CCSM or CESM over the years. And so I'm especially thankful to the Polar Climate Working Group. For they literally adopted me in addition to my code. And Marika, most of all, because we were co-chairs for so long. We worked together for so long. That's just fantastic. And as I think you've all gathered from the talks, eventually the CI simulations produced by CCSM were widely recognized as the best in the world. And that was because of the Polar Climate Working Group. That's not something that I could ever have done by myself. And then I put this picture in because I know a lot of you would appreciate it. But in my role as Polar Climate Working Group, one of the trips that I got to go on was to Japan. I got to visit the Earth simulator in Japan with Byron Boville and Frank Bryan. It was just the three of us, a delegation of three who went out there. And that was an amazing trip. It was like 2.5 days long. We went out there and came back, and I was like, did that really happen? But on the flight back, Byron told me about his cancer. And so this is a very special picture for me. And then, of course, there have been lots of other wonderful opportunities because of the Polar Climate Working Group connections. And I originally put this slide without the names. And I was going to say, do you know who those people are? This is one of my favorite pictures from the ice camps. And this must have been the first one, the first ice camp. I was lucky to get to go to both of them. So this was really fun and really special because it was bringing the modelers and the observationalists, the measurement people together to teach each other what we do. And so the measurement people would take us out under the sea ice and say, oh, here's how you measure thickness, and here's how you measure albedo, and those kinds of things. And then in the afternoon, we'd go to the classroom, and then the modelers would try to explain to the observationalists what we actually did in the model. And you're like, really? But I thought it worked really well. Oh, that's what that one was. You've seen this picture a lot. That was a really cute picture. It was taken there in Barrow. But just off to the side here, Hayo Aiken is standing there, and he is laughing his head off because you can kind of see it in the picture, but the brine is draining out of the ice core right down my leg. And he says, your baby's peeing on you. So that was funny. Okay. Yeah. And that was my team. It has Melinda on it, who's here. Yeah. Is Jen? Jen is this evening. Okay. Yeah. Okay. Yeah. Okay. So, I also want to recognize my colleagues at LANL. Jerry Brackbill, you heard from earlier. He's not in COSM, but he has been a mentor for almost my whole career, even though I told him at the beginning that I didn't need him as a mentor. He has been. And most of all, he's been a really good friend. I don't know if I can do this. Let's see. Yeah, okay. So Phil Jones, oh, the cursor's not showing, is it? All right. Phil Jones is way over there on the far right side. He took over COSM leadership from Bob when Bob retired, and I'm grateful for him for that because he's the one who was writing the proposals. You know, he asked us for a paragraph or something. But perhaps even more importantly, he wrote POP's infrastructure. And POP's infrastructure is what SICE was built on. So we wouldn't have SICE if we didn't have Phil. So he was really, really important. And I'm also so happy that Scott Elliott and Nicole, who is here, they took that leap into sea ice biogeochemistry. Scott's the one with the white hair in the middle, and pretty stern. But that was, I don't know why you're giving me credit for that. I helped, but they were the ones who really took it where it needed to go, because I don't know anything about biogeochemistry. And Matt Maltrude is also in that picture somewhere. The center top, yeah, kind of in the back. So he advocated for and also worked on the biogeochemistry for years and years and years, and he still is. And I really respect him for all the work that he's done, but I'm also thankful to him for his enduring cheerfulness. He's always, making us all laugh. And he has always brought levity and perspective to many days for me when I needed it. And I did meet him within my first week at Los Alamos. So he's known me for a long time. And then Andrew hadn't gotten to Los Alamos by 2012 when this picture was made. And part of the reason that these pictures are weird, we're not allowed to take pictures at Los Alamos. And so all of our pictures have to be off-site. So there's kind of a weird combination. But anyway, I'm grateful to Andrew for your intellectual leadership and your friendship. That's so important to me. Of course, our collaborations began long before Andrew got to Los Alamos, and it's many, many years. Not that one yet. Okay. I also want to thank my students and my postdocs. There really haven't been very many, considering I've been at the lab now for 30 years, and I only have a handful. But it is a laboratory. It's not a university. Technically, as Bill said, he was my postdoc, joint with John Dukowitz. But John did all the mentoring work, I think. Bill had been studying sea ice with Norbert Untersteiner for at least as long as I had been looking at sea ice. And he understood it way better than I did. And so I've always considered him a colleague rather than a postdoc, right from the beginning. And likewise for Adrian Turner, we haven't really seen or heard much from him here, but I hired him because he's the one who understood mushy layer physics. I didn't understand it, and I'm still learning things about it. But Darren Como came to the lab for 3 summers in a row as a graduate student from the University of Arizona. That was our connection. And again, thanks to Phil, I went and said, Phil, is it okay if I work on an iceberg model with a summer student? And Phil said yes. And so we just did it for 3 summers. And that iceberg model is still not in the climate models, but I think it will be, hopefully soon. I don't know. But actually that iceberg modeling work was inspired by the trip to Antarctica and the icebergs out just in front of the Ronnie ice shelf that Steve Ackley showed. where, you know, from the ship, we could tell, you know, the sea ice was piling up on one side and opening a Polonia on the other side. That's what I wanted to simulate, and that's what Darren and I did. So, okay, and then finally, Jorge, since you left research, I'm not sure if you were aware, but your parameter sensitivity study, your paper on that, that is now the go-to reference for sea ice parameters. It's like, it was so cool. And Jorge just jumped right into AI and ML on his own initiatives, not something I knew anything about, and started doing that stuff. And it was like magic to me. And so I'm, yeah, it was new. Yeah. Yeah. So Marianne, you two should talk. Okay. So now I'm going to go on to the SAIS Consortium. There's a lot of pictures there, a lot of people, and I'm not going to try and name them all, but the SAIS Consortium has truly been a gift. And so I'm really grateful to all the agency leads across all the agencies, including DOE, who are willing to let their staff members spend their time collaborating on this project. I appreciate all the team members up here in the upper left for their willingness to share their time and their expertise and their work toward a common collaborative vision. Tony's daughter is playing a concert at the Kennedy Center. And so I don't blame him at all for wanting to go to that. But so that's why you haven't heard from him, but his name has come up over and over and over. And he has been working on this since PCM days. You know, when Yusha was first putting EVP in, Tony was there, he was part of that. And so we have worked together that whole time. And he's sitting on my, what is that? That's the left in this picture, the way you're looking at it. Alice, oh my gosh. She came in and just went for it with the consortium, getting things set up. You mentioned that in your talk, and that was also so helpful. It's exactly what we needed. And thanks to NCAR for funding her to do that. Whoever, I don't know if that was Peter or who it was at the time. Let's see, I'm going down my list here. And then I wish I could go through everybody in that picture, but I don't have time. And so I'm going to do a blanket statement that, you know, all of you, thank you, Rika, Dave, everybody. But a special call out to Dorothy Koch and Shujing Davis and Dave Bader again for giving the consortium the DOE stamp of approval and providing guidance to me in running it. I've had a few phone calls with them saying, what do you think I should do? Okay, so there's not enough time to mention everyone who's contributed to the success of my career. I apologize if I'm leaving somebody out and you don't take it personally. But please know that I'm grateful to every one of you. I could not have built a sea ice model without the rest of the community. That's for sure. Okay. So the question of the day is, what are you going to do in your retirement? Right? All right. So first of all, I'm going to keep doing the things that I love to do. And one of those things is the SAIS Consortium. All right. So I'm just planning to keep going with it. Yay. But one thing that I will do is kind of rebalance things more to my liking, which actually includes doing more on the SAIS Consortium and less lab management kind of things. So I want to continue helping all the various institutions with whatever they need help with, to the extent that I can, right? And I'm sure that many of you have seen my GitHub avatar up there. I'm going to let you in on a little secret, which is the reason why I'm smiling in that photo, is that I'm standing next to my airplane. And this was a photo made by Marianne on one of our, this was actually an overnight fly out to Angel Fire. Yeah, so she took that photo. And I use it on GitHub. That's where it is. But I should also thank my mother, her name is Harriet Coburn. She's in Tennessee. But she taught me as a little kid that even mothers could fly. She is a pilot. So one of the other things that I wanted to mention, I wish I'd thought of it and put it in the slide deck, but I think it was Mary Ann's email that had a quote at the bottom of it, which I absolutely loved. I don't know, well, I don't know if it was you or if it was Eileen. It might have been Eileen. It might have been Eileen. But it said, you know, some guy told me I fly like a girl. And I told him that if he worked a little harder, he could too. Yeah. So, all right, moving on. So music has always been a solace for me. I really enjoy playing my French horn. I met Steve playing music. He's a tuba player. And I love playing in groups like orchestras and brass bands and wind ensembles. And if you think about it, that's a different kind of collaboration where you're creating something beautiful together. And I just love doing that. I'm looking forward to more hiking and biking and camping in our R-Pod and under the wing of the airplane. We sometimes do that. And also more gardening. Aaron mentioned this one. I come from a Tennessee farming family. I actually have a farm in Tennessee, and gardening is really important for me. So we're going to be doing more of that for sure. And best of all, I want to spend more time with my friends and my family. And several of the pictures that are up here are photos from flying trips that we made where we just went out and visited people. Rick Aller, the NRL crowd, mentioned that we stopped in for lunch at Stennis Space Center on one of our flights. It's like, this is fun. So Mary Ann's in there again. We've done a lot of flying together. That was a weekend trip that we flew to Kanab, Utah, and rented a houseboat and sailed around on Lake Powell and then flew back. But lots of fun. I know some of you are going to recognize people like Julie McLean, the Los Alamos. I don't know if any of the older Los Alamos people are still here. Manjeet. He was always, in addition to going to lunch with Jerry, we would go to coffee every morning, and Manjeet was that crowd. And every day he was like, "You owe me a cappuccino." And so the trip that we stopped in Monterey and visited Andrew, but then we went up and flew by Manjeet's, and I bought him a cappuccino. So anyway, if you tell me where to find you, I might just come and visit you too. I'd love to do that. And then finally, I want to thank my husband, Steve Ross, who's here, for being my cheerleader and my luggage porter and my co-pilot and my best friend for the last 25 years. So it's been a wonderful journey with all of you, but I'm not completely disappearing. I will still be around. And there is one more thing that I want to say, and I don't have any pictures for this, but just in consideration of the stress and the uncertainty right now that's going on. In graduate school, I fell totally in love with clouds and weather and hurricanes and tropical cyclones. And, as a graduate student, it was fabulous. It was wonderful. This is what I wanted to work on. But then I'm going to have to read this because I don't think I can say it. At the end of my PhD work, my graduate advisor told me he never wanted to see my name on any paper having to do with hurricanes, ever. And that was really difficult to hear as a graduate student. you know, just finishing school, starting a career, that was the thing that really was the blow to my confidence. And it took a good 10 years to get that back. But I followed Mac's advice, and I did my best to create a usable and useful sea ice model with lots of help from all of you. And 30 years later, I've been much more successful than I could ever have been in the hurricane world. So I know many of you are kind of like me in that it would be sad, but not necessarily devastating to have the work that you love suddenly come to an end. Because you've already had a long and successful career. But for others of you who might be younger, what's happening now has to be really, really scary, you know. But what I want to say is that every one of you is extremely smart and talented, and you can apply your skills and talents to any number of satisfying activities that can make this a better world to live in. And so I do hope with all my heart that you can continue down the path that you have chosen. But if it turns out to be a different path, then I know you'll do a wonderful job wherever it leads you. And finally, if you happen to be writing a hurricane paper, give me a call.
Amazing. Well, unless there's any other comments or thoughts, yeah, there's a lot there. Then I guess we adjourn to Marika's place. So